Kraken Mare is Titan's largest sea, Saturn's moon, a black ocean of methane and ethane under an amber sky that dissolves edges and steals depth. What is unsettling is not noise or violence, it's the opposite. The landscape reduces the palette to blacks and ochres, the horizon turns into a gradient with no line, and the surface alternates between mirror and velvet. A calm sea that doesn't give enough clues is, by definition, a problem. And that is what earns this place the label of scary. It doesn't threaten with a blow. It threatens by carefully removing everything that normally helps you grasp where you are and what is happening. The first layer of this uncanniness is material. At the typical temperature of Titan's North Pole, around 90-odd Kelvin, what plays the role of water is a bath of hydrocarbons. Liquid methane and ethane do not tolerate the same repertoire of materials as water does. Elastomers stiffen, common lubricants crystallize, plastics lose useful elasticity. The intuitive solution, heating, contradicts the very need to measure. Too much heat creates a local film of gas around surfaces, altering buoyancy, drag, and acoustic readout. Survival and observation become a millimetric negotiation between keeping systems warm enough inside and preventing that little private summer from leaking outward and distorting the medium. There is no drama, but there is mandatory precision. The second layer is optical. An atmosphere denser than Earth's, saturated with organic particles, filters the light and scatters what remains. Shadows are weak, outlines don't define, contrast becomes a rare commodity. A sea that on Earth is read by colors, foam, and the horizon line, here demands a new grammar of discrete signals. Uniform, continuous sheen indicates a calm sheet. A subtle granulation in the varnish betrays wind transferring energy to the surface. Tiny, irregular scintillations often precede methane drizzle. These are whispers, not snaps. And an environment that communicates in whispers punishes careless listening. It is very easy to take a mirror for a path and a shadow for a shore. Surface dynamics reinforces the trap. With gravity about 1/7 of Earth's, waves tend to lengthen their period and lower their crests. Instead of breaking water walls, black swells appear that run under the sea's skin like a slow breath. The result is a paradox. The smoother, the less information. Without a bright sun trail, without surf, without familiar lapping, distance and speed estimates lose calibration. A channel that from afar seems broad becomes a throat up close. The bay, apparently open, reveals a shallow step that holds invisible. It is a sea that demands going slowly, not to avoid its force, but to give the eye time to learn its language. When vision fails, measurement engineering steps in, and Kraken Mare makes that step delicate. Low-altitude radar sees little, the organic haze blurs, the dark liquid reflects poorly, contours lose firmness. Sound helps, but the propagation speed in methane and ethane varies with nuances of temperature and composition. A slightly colder layer bends paths, delays returns, and fabricates phantom depths. From time to time, magic islands appear, patches that show up and vanish in the data over hours. They may be thin plates of hydrocarbon ice, organic foam produced by agitation, bubbles released from the bottom, or wave alignments acting as temporary mirrors. One need not choose a single culprit. In an environment that changes slowly, several explanations coexist, and the behavior observed depends on season, wind, angle, and moment. The prudent procedure ceases to be trust the best instrument and becomes build consensus among instruments over time. Time, incidentally, is the silent agent that glues all the other dimensions together. Titan's North goes through long seasons. Slow changes in lighting reorganize winds and clouds. When it rains methane. And the rain barely announces its arrival by sound. The air's density and the nature of the liquid absorb frequencies that, on Earth, would betray a storm. The drizzle wets surfaces, forms a film. The wind dies down. That film freezes at the edges. Friction changes discretely. Consumption rises by modest percentages. Range shrinks by minutes that seem little and cease to seem so when added up. The risk here is not in the present minute, it's in the accounting that it feeds. The shores and the bottom extend this reasoning. Titan manufactures in the high atmosphere complex organic particles that fall over ages and accumulate like dark sand. In Kraken, those tholins redraw the coastline with a patient tide. These are not dramatic tides, but the combination of level variation with wind and channel geometry suffices over days and weeks to turn a ramp into a step, a shallow bank to migrate half a meter, a choke point to change its signature. In one stretch, the beach looks like cold cement, hard, smooth, predictable. A few meters ahead, the texture turns into oily flour that yields slowly. Maps are photos of an ongoing conversation. What held during the last campaign now needs to be verified once more. Operational humility isn't etiquette, it's method. There is also a detail that doesn't appear in the landscape and yet sets the tone of any planning: communication delay. What goes from Titan to Earth and back does not do so in minutes. Decisions arrive when the place that will receive them has already changed a bit. One works by plans, not reflexes. This turns slow geography into a temporal labyrinth. You choose a route now for a sea that may, when the order is finally executed, have placed a shallow step where there once was a passage, or received a drizzle that discreetly alters drag and consumption. Fear here has the color of statistics. It is not "it will go wrong," it is "if it goes wrong, notice late and correct with less margin." If all this sounds like an obstacle course, it's worth remembering the reason this place matters so much. Kraken Mare allows us to observe a complete hydrological cycle that does not use water. Clouds, rain, channels, deltas, and seas operating with hydrocarbons, which means measuring slightly different compositions in coves and bays, observing how waves are born when gravity is small and air is dense, inferring how energy changes hands between atmosphere and surface in a scenario that changes the terms of the problem. The magic islands themselves cease to be an anecdote and become a recurring natural experiment. Something appears and vanishes under conditions repeatable enough to test hypotheses about thin ice, foam, or wave arrangements. What makes the operation risky is what gives value to the data. It helps to compare with terrestrial seas to calibrate intuition. Down here, the sea warns where it is rough. On Titan, the sea avoids saying anything. The silence is not an absence of processes, it is an excess of signal attenuation. And in this silence, the small contradictions become guides. The apparent calm that reduces noise also reduces information. The heating that keeps instruments alive is the same that, if overdone, fabricates gas bubbles and ruins measurements. The map that shows a safe path is by definition a portrait of another day under another light. In each case, the correction is the same. Trade quick certainties for slow consensus. This philosophy translates into concrete procedures. Careful approaches when the surface turns into a mirror to avoid entering throats in disguise. Cross-checks before accepting a very uniform bottom, knowing that cold layers can delay the acoustic return and feign greater depth. Thermal routines that prioritize stability over comfort so as to not cook the surrounding liquid and not to create a gaseous layer that lies about buoyancy. Route reviews that take into account hours of history, not just the snapshot. Everything sounds unheroic because it was designed so that nothing dramatic happens, and that is exactly the point. If curiosity asks about dimensions, the general portrait helps set scale without relying on point numbers. Kraken Mare covers an immense area and stitches itself to other basins by corridors and choke points. Depth jumps from shallow stretches to valleys hundreds of meters deep. Straits control flows between bays like natural sluices, but without a lever. In mental language, it helps to think less of an ocean and more of a liquid archipelago, where each corridor breathes, albeit slowly. Between any two shores, instead of a ruler, there is a negotiation. Meteorology closes the risk sketch with an almost literary detail, but a fundamental one. On Titan, rain is almost mute. There is no clear patter on the surface, no symphony of drops. There is a gain in humidity, a thin film, an altered sheen, a number that climbs a little and accumulates where it counts, in the range. It is a reminder that what is scary in this sea is not what is seen, it is what ceases to be seen, and at the same time keeps acting. The amber sky looks like a gentle filter. It is precisely that filter that hides contrast. The black varnish looks like a promise of stability. It is that varnish that deprives the eye of the texture that orients. Looking from afar after understanding all this changes the relation with the image. The dark rectangle surrounded by soft margins no longer is a strange lake. It is an alien climate machine running at low RPM. The minimalist beauty, a sea with practically no foam, a coast of organic dust, a sky that gives back only what is needed, does not remove a gram of the place's technical severity. Scary here is not a synonym for spectacular, it's a synonym for indifferent. The environment doesn't try to topple anything, it simply doesn't cooperate with anything. That is harder because it shifts all the responsibility to the one who measures, interprets, and decides. Leaving Titan with this lesson naturally sets up the contrast that comes next. If here the sea is liquid and cold and fear is born of subtraction, less light, less noise, fewer clues. There on Venus, the sea is the atmosphere itself, dense, hot, chemical, insistent. There, danger doesn't hide, it occupies every cubic centimeter of air, squeezing, reacting, accelerating wear. The dialogue between the two worlds is didactic. One teaches you to read whispers, the other forces you to withstand shouts. Venus's plains are the direct opposite of Titan's cold silence. Here, the sea is not liquid, it's the air itself. The surface is an open field of rocks and basalts, and yet what dominates is not the solid landscape, but the column of atmosphere that weighs on everything. The image is paradoxical from the first contrast. It's the neighboring planet, a near twin in size, and yet the ground is wrapped by a pressure about 92 times Earth's, with temperatures near 465 degrees Celsius, numbers so high that lead, which on Earth is a metal, here is something that flows. There is no cinematic storm, no dust tides rising kilometers. The threat is the constancy, and it is this character of an environment that pushes from all sides at once that makes the Venusian plains one of the most frightening places in the solar system. What sets the tone is the combination of heat and pressure. At 92 atmospheres, the carbon dioxide in the air sits well above the critical point. It behaves like a dense fluid with properties that don't fit neatly into the comfortable drawers of gas or liquid. This density changes everything: how heat moves, how surfaces exchange energy, how materials age. Radiators, for example, stop throwing heat outward efficiently because outside is already too hot. Convection, which down here usually saves electronics and engines, there works like a hot hand rubbing the equipment. Engineering that would work in a terrestrial desert fails on Venus, not for lack of ruggedness, but because of an excess of environment. Every second, the air works against every joint, every weld, every seal. Pressure alone would earn respect, but it is the marriage with temperature that frightens. A useful number to calibrate intuition. 92 atmospheres is like being close to a kilometer deep in Earth's ocean. Underwater, at least there is water to carry heat and stabilize quick variations. On Venus's plains, the medium is supercompressible, super-hot carbon dioxide, permeating cracks and pressurizing voids with an insistence that no laboratory reproduces with the simplicity of the real world. Even familiar alloys change their mood. Common solders, which here soften at 200 degrees Celsius, would lose integrity upon arrival. Elastomers that seal pipes shrivel, lose elasticity, and cease to be elastomers. They would become only temporary shapes of soft material trying to exist where they shouldn't. For those who imagine the sky a white oven, the light at the surface surprises in the opposite direction. It's amber, diffuse, almost sad. Almost all of the sun's brightness is reflected or scattered at the top of the sulfuric acid clouds. What reaches the ground resembles a constant, stifling afternoon that does not turn into a cool night afterward. The greenhouse effect is so extreme that the difference between day and night at the surface is small. The air holds heat like a blanket that never leaves the planet's body. And then another contradiction grabs attention. Although Venus receives less direct light on the ground than some terrestrial deserts on a clear day, it is the hottest planet in the solar system, hotter than Mercury, which is closer to the Sun. The explanation is technical and implacable. Heat enters slowly, but does not leave. It gets trapped and redistributed by a thick atmosphere that, at high levels, runs like a river around the planet. This race, the so-called super-rotation, is a spectacle that happens above the plains. At the cloud tops, winds circle the globe in a few Earth days, much faster than the planet's absurd retrograde rotation that takes about 243 days to spin once. On the ground, by contrast, gusts are slow, but slow only in speed. With densities dozens of times greater than our air's, a 1 meter per second breeze exerts forces and pressures equivalent to those of a strong wind down here. These are forces that do not leap dunes like on Mars, but push objects with a stubbornness that does not photograph well. The scene looks still, the mechanics are not. Chemistry adds an extra layer of discomfort. It is said that it rains acid on Venus, and this is true in the clouds. Droplets of sulfuric acid form and dissolve, fall and rise in cycles of condensation and evaporation. Only none of them reach the plains. A few kilometers above the ground, the heat is so intense that the acid evaporates. What deposits on the surface is less a liquid assault and more a continuous bath of reactive gases. It is an elegant cruelty. Little remains of the drama of a corrosive drizzle, but much remains of corrosion. Sulfates and oxides react slowly, like chemical scratches that never heal. Science must step in with materials and coatings that, even without receiving drops, can withstand an atmosphere that insists on participating in surfaces. The word resurfacing appears in any honest explanation of Venus, and it is uncomfortable because it denies the accumulated time of craters. It suggests large, perhaps episodic events that erased old marks and left the ground with a younger average age than one would expect. Whether it happened in one event, in several outbursts, or in a continuous process, the debate is open. The plains hold the clue, and at the same time, hide it under the same thermal varnish. There are discrete monuments in this apparent flatness, shield volcanoes that resemble perfect hills, circular cauldrons called coronae, domes that look like stacked pancakes with diameters of tens of kilometers. On any other planet, the simple catalog of these objects would yield a parade of superlatives. On Venus, the camera pour and direct light, the heat, and the pressure drain the image's dramatic energy, and everything becomes studi. This trade of spectacle for specificity is, curiously, part of what makes the place frightening for anyone thinking of operating there. Nothing promises a clear signal. Everything promises a series of constraints that only work if the reading is precise. If the ocean analogy makes sense, so does the thermal one. Imagine trying to cool equipment in a bain-marie that is already above tin's melting point. Radiating heat does not help if the surroundings radiate back. Ventilating does not help if the air mass injects heat instead of carrying it away. Only strategies remain that on Earth we consider extravagant. Electronics designed to operate hot by design. Solders and alloys that don't melt by usual standards. Insulation packages that are not blankets to retain heat, but to slow exchange with an exterior that insists on heating. Each solution carries a contradiction that holds the mind. What on Earth would be called efficiency, here becomes risk. What on Earth would be waste, here becomes survival. Venus's slow rotation brings another curious effect closer, almost poetic but physically severe. The very concept of noon loses practical usefulness at the surface. With days longer than the year, the atmosphere takes over the role of the clock. Thermal waves and atmospheric tides, yes, there are tides in the air, induce patterns that don't match what Earth intuition calls morning and afternoon. For instruments that rely on predictable heating and cooling cycles, this displaces relief times. Rest does not come at night, because night, in practice, does not cool. The planet trades the clear, dark alternation for an amber persistence that wears down like a bright lamp left on in a closed room. The rhetoric of crushed landers tends to exaggerate the mechanical role and forget the electrical. On the plains, electronics are the enemy of heat. Without specialized semiconductors, transistors flee their ideal curves, leakage currents increase, thermal noise invades signals. In other words, it is not only a matter of withstanding pressure and not melting as a whole, it is a matter of thinking with circuits that under our conditions we would never need to imagine. If there is an intellectual challenge that Venus throws down, it lies in this invitation: design brains that reason hot. Fear here is very little cinematic and much more mathematical. In parallel, the apparently monochromatic soil hides complexity. Basaltic grains, altered rocks, minerals that stabilize unusual compositions at these pressures and temperatures. If everything seems orange, it is as much because of the filtered light as the surface returning preferred wavelengths in this bath of hot air. Historic photographs show low horizons, flattened blocks, nothing spectacular, the nothing that is in itself the most honest scenery of a furnace. Alongside this nothing, there is tectonics without plates like ours, but with features of compression and stretching, long ridges, valleys that meander, signs that the interior pushes and slackens the crust in its own way. Nothing shakes like in a big movie earthquake, but almost everything has been displaced at some point, slow enough to not make news, large enough to rewrite maps. It may seem that corrosion would be the star, but chemistry plays against the easy stereotype. The sulfuric acid that dominates the clouds does not bathe the plains, it evaporates beforehand. What prods the surfaces is more subtle: sulfur dioxide, scant water vapor, reactions that cook minerals in long-term baths. There is no dripping rust, but there is an air within tension. And this air imposes an uncomfortable truth. Unlike environments where the risk chain has a recognizable weak link, a cable, a joint, a button, on Venus, the whole chain works near the limit. One does not choose the critical point, one lives with many. The direct question, why is it scary, earns answers that protect each other. Because a small deviation becomes a big failure without warning. Because nothing cools at the pace we are used to. Because air density turns a breeze into force. Because the atmosphere's clock does not match the operator's time. Because the ground tells a story of lava and compression without offering a simple alphabet to decipher it by sight. Because all this happens nearby, not on an exoplanet light years away, but next door, on a travel and communication scale that would seem far too comfortable for the level of hostility waiting at the destination. And yet the scientific value of the Venusian plains is proportional to the discomfort. There, the hypertrophy of the greenhouse effect is studied without metaphors. There, terms like supercritical and superrotation are taken out of abstraction, and instruments are put in the very place where these concepts shape the landscape. There, one observes a style of volcanism that does not copy Earth, but converses with it, offering an inverted mirror of processes that may have occurred here in another era. There one learns above all to think engineering outside the practices our atmosphere taught us to consider natural. It is scary in the most fertile sense of the word. It forces reimagination. The closure of this sketch is not a moral, but a synthesis of the physical chain. The dense, superhot air defines how to see, measure, and build. The way of seeing, diffuse light, few edges, constrains confidence in maps and telemetry. The way of measuring, radars, acoustics, consensus among instruments, demands time and redundancy. Time is drawn by an atmosphere that does not cool. Redundancy adds mass, and mass suffers under pressure and heat. Nothing in this chain is spectacular in isolation. Everything is decisive when added up. Fear arises precisely from the fact that the environment need do nothing but be itself to win. Leaving Venus's plains, then, is not a dramatic relief. It is a change in focus. From a world where the air squeezes and cooks, the next step is to look back to the cold, but a cold with energy underneath. Ice fractures that jet plumes, margins where white misleads as much as amber misled here. The logic remains the same. Understand how matter, light, and time tie together the experience of a place. The scene changes from constant heat to active ice. The lesson does not. In both, the most frightening landscape is the one that forces you to trade habits for attention. Enceladus's tiger stripes are 4 large, almost parallel fractures at the South Pole: Baghdad, Damascus, Cairo, and Alexandria Sulci, that extend for hundreds of kilometers and concentrate the satellite's greatest activity. What makes this region truly dangerous is the combination of 3 factors: active fissures that open and close with Saturn's tides, cryogenic jets that launch water vapor and ice hundreds of kilometers high, and a mechanically unstable terrain covered by constant fallout of fine particles. There is ice everywhere, but the behavior resembles a pressurized geyser system coupled to a global ocean. Small on the planetary scale, Enceladus defies intuition by exhibiting energetic processes typical of much larger worlds. The fractures work like valves. Enceladus's elliptical orbit and resonance with Dione impose cyclical deformations. The South Pole undergoes traction and compression along the orbit. When tension opens the fissures slightly, pressure in the underlying ocean finds a path to the surface and the jets intensify. When it closes, activity diminishes. This periodic modulation, stronger plumes in certain orbital phases, weaker in others, makes the region a moving target. No measured value is fixed. Everything depends on the moment. Operationally, this means forecasts must take into account tidal state and hours of history, not just pretty images. The jets are multiple and fine, closer to sprays than single columns. The ejected material is mostly water, partly as vapor, partly as ice grains of varying sizes. Mixed in appear salts, such as chlorides, carbonates, nanometric silicates, and organic molecules. The presence of molecular hydrogen measured in the gases indicates water-rock interaction at the ocean floor, compatible with hydrothermal activity. On engineering scales, none of this is mere scenery. Abrasive particles and condensation on cold surfaces make sensors lose efficiency, radiators freeze by deposition, and mechanisms seize by adhesion. The word snowstorm describes the look, but not the impact. This is a fine, persistent sandblasting that over time changes the behavior of everything left exposed. Very low gravity creates an additional paradox. Escaping Enceladus requires speeds on the order of hundreds of meters per second. Some of the jet material reaches that and feeds Saturn's E-ring, but a significant fraction falls back as fine snow. The result is a precision grime cycle. slow but steady accumulation on any protrusion or cavity, altering surface roughness and friction. The same gravity that makes landing maneuvers light increases the risk of unwanted hops. Too small an impulse fails to correct trajectory. A bit more throws a vehicle tens of meters up. Nothing helps more than predictable terrain, and Enceladus's south pole offers the opposite. The tiger stripes are not mere lines on a map. They are trenches with raised rims, steep walls and floors full of blocks. The temperature difference between the stripes and the surrounding terrain is real. Measurements show the fractures are significantly warmer than the ambient ice, though still extremely cold by Earth standards. This less cold temperature betrays heat flux from below and changes local mechanical properties. Warmer ice is less rigid, more prone to deform and yield, which explains part of the mobility of the rims and the appearance of small secondary faults. On a day of favorable tide, a rim apparently stable can lose support and collapse by decimeters. For instrumentation leaning there, that suffices to shift angles and ruin calibration. Temporal variability complicates everything one wishes to keep constant. Aerodynamic thrust in the near vacuum, wheel torque, which depend on snow cohesion, and machine vision, which needs contrast. Fail-out of micronized ice changes reflectance over hours. What was a striped texture for optical navigation becomes a homogeneous carpet. Faint sources of static electricity, favored by dry, cold grains rubbing, interfere with sensors, demanding careful grounding. If the goal is to collect samples directly from the jets, another dilemma arises. Getting too close increases flux and volume, but also the risk of impacts by larger grains. Staying too far reduces contamination, but yields a less representative sample. The sweet spot is not fixed. It migrates with the tide, with the jet's vent orientation, and with the hour. From a geophysical point of view, the whole set is coherent. A global saline ocean, an ice shell of variable thickness, tending to be thinner at the South Pole, fissures that descend nearly to the sea and conduct vapor and grains driven by pressure difference and internal heat. The presence of molecular hydrogen, nanometric silica, and phosphates in plume grains supports the idea of hydrothermal vents on the ocean floor, hot water percolating through ultramafic rock, generating reducing chemistry. For astrobiology, that is the meeting of ingredients of interest: liquid water, chemical energy, nutrients. For operations, it's another list of demands: materials compatible with salts, ice control in sampling inlets, and thermal discipline to avoid sealing off one's own intake. Local topography adds route risks. Between one stripe and another, there are undulating plains covered by recent snow. The sheer strength of the surface layer is low. Wheels dig, sleds anchor, feet sink a few centimeters before finding hard ice. Near the fractures, roughness grows due to thermal fracturing, faceted blocks, fresh edges, steep ramps that require controlled angles to avoid initiating slides. Descending into the vicinity of a fissure means living with lateral thermal gradients, one side a bit warmer, the other colder, which creates stresses in the vehicle itself and small gas puffs that lift ice dust and return it to intakes where it shouldn't be. There is an orbital component that cannot be ignored. Enceladus crosses a particle population in the E-ring that it itself feeds. Passing through specific planes implies fluxes of high-velocity grains that, depending on trajectory, can wear exposed surfaces and darken lenses. In low gravity, every grain that sticks counts. The difference between an operational radiator and one clogged by deposition is measured in hours in an environment without an external heat source. Common strategies on the Moon, shaking, blowing, sweeping, have almost no analog here. There is no air, and too much vibration can cause loss of contact or HOTS. Useful contradictions help read the place. It is an icy world, but with enough heat underneath to maintain an ocean and mobilize fissures. It is small, but has dynamics capable of launching material into space and sustaining a planetary ring. It is a low-gravity terrain where forces are gentle, but that gentleness turns any fine correction into an exercise in extreme control. It is, finally, a target of extremely high scientific interest, with plumes that bring samples from the interior up to the high exosphere, but that demands precisely keeping distance so as not to degrade the data with one's own heat and contamination. The modulation of the jets with the orbit deserves separate attention. At maximum tension phases, the effective opening of the valves increases and the flux rises. In compression, the reverse. This not only alters plume visibility hundreds of kilometers up, it changes the South Pole's meteorology on our scales. Particle fallout, albedo, surface temperature measured on the flanks. It is the cryogenic version of a coast where the tide changes at each visit, with the difference that here the tide moves ice and gas, not liquid water in sight. On the chemical side, each component implies a care. Salts mean hygroscopicity and potential corrosion at exposed interfaces when there are thermal cycles. Silica suggests abrasion in bearings and valves. Organic molecules adhere and smudge optical surfaces. Molecular hydrogen indicates a reducing environment. Along with carbon dioxide and trace ammonia, it can trigger undesirable reactions in unsuitable materials. The solution is not a single miraculous coating, but a set of choices: short intake paths for cold samples, localized heating to prevent freeze-up in filters, grain launchers to clean windows without contact. Why is all this scary? Because nothing here fails theatrically. The tiger stripes as a system win by accumulation. A bit of ice on radiators reduces heat rejection capacity. A film on lenses reduces contrast. A salt deposit glues a cap. A wheel loses grip. A small hop knocks antenna geometry out. A wrong angle exposes an inlet to spray at the moment of maximum opening. The error will, almost always, be small and sequential, and it only becomes clear after it adds up. In environments like this, robustness is less armor and more discipline. Do less but consistently. Measure more but cross-checked. Approach and back off according to the orbital cycle, not according to will. The location's technical merit equals its risk. The plume offers direct sampling of the ocean without drilling ice. Temporal variations test models of tides and ice rheology. The composition of grains and gases reveals rock floor chemistry and possible hydrothermal activity. The operational price is working with tight limits on mobility, energy, and contamination. In short, it is an exceptional laboratory that demands exceptional procedures. Next, the focus leaves ice and goes to rock heated to extremes, the terminator of 55 Cancri E, where day and night meet with violent gradients and chemistry potentially dominated by rock vapor. 55 Cancri E, terminator, magma versus night, far. This is the lava world of the moment, a super-Earth that goes around its star in less than 18 hours, and very likely always shows the same face to the sun, like the moon does to the Earth, only in extreme mode. On one side, heat sufficient to keep rock molten. On the other, a night that tries to cool and even capture part of what evaporates on the day side. The real interest is precisely at the edge between these two regimes, the terminator, the belt where day and night meet, the most unstable terrain, and therefore the most dangerous to imagine operating in. This is where opposing processes touch: winds, if there is an atmosphere, currents in a shallow ocean of magma, and falls of rock condensates that solidify in the dark. 55 Cancri E is small enough to be rocky and large enough to hold heat for a long time. It is so close to the star that it completes an orbit in 17.7 hours. It's the definition of ultra-short period. Recent observations with James Webb near Cam and Mare reinforced the general picture. The day side shines strongly in the infrared, and the contrast with the night is large, suggesting poor heat redistribution, sign that either the atmosphere is very thin or energy transport is inefficient, or both. There are hints consistent with a tenuous atmosphere, perhaps rock vapor, perhaps CO2 released from the magma, but the visits show variability from one epoch to another, which complicates final sentences. In practical terms, the planet does not behave the same way every time it is observed, and that alone already makes the Terminator a place unstable by definition. The frightening part begins with the numbers. In different observations, the day side has appeared with brightness equivalent to temperatures around 2300 K in older measurements, and with Webb varying from hundreds to over 2000 K at certain wavelengths. That is heat enough to keep silicates partially molten and volatilize species like silicon monoxide, SiO, and sodium, composing an air of rock that can circulate and condense on the dark side. More important still, some of the hottest measurements still don't match what would be expected for bare rock, with zero heat transport, which supports the idea of a sheath, even if thin, capable of tweaking the thermal balance. The picture that emerges is of a planet that sometimes breathes more, sometimes less, trading energy between phases irregularly. When thinking about the Terminator, it is advisable to chain the processes without separating atmosphere from surface too much. If there is a gaseous film of rocky compounds over the day side, it is born from the magma, literally evaporates from the liquid. Near dusk, where the star's flux has already fallen, this gas begins to lose energy and tends toward condensation. Heavier molecules turn into grains. The grains fall back and feed the surface with a dust that hours earlier was vapor. On the night side, where cooling is stronger, this cycle should be even more efficient. What left is out whiff of lava from the hot side becomes dew of rock on the cold side. Without a robust atmosphere to mix everything evenly, the recycling stays local. Material rises, travels little, returns. And the Terminator is the corridor through which much of this exchange happens. This produces practical contradictions. Air, even thin, helps transmit heat and could soften the gradient. But if it is made of rock vapor, it cools and vanishes precisely where it would be most needed, leaving zones with behavior nearly vacuum-like. A shallow ocean of lava would facilitate surface redistribution, but magma viscosity increases as it cools, and approaching the Terminator, the stuff thickens and stalls. If there are winds, they can blow ash and gases from the hotter areas toward the edge of night. If there are not, the transfer falls to waves and magma tides, driven by density differences. In all possibilities, there is no lasting stability. The very mechanisms that bring sides closer also create seams that renew themselves every rotation. A useful reminder about scales. 55 Cancri E receives a stellar radiation path far greater than Earth's, and synchronized rotation means the noon of a fixed point on the day side is permanent. At the Terminator, the light arrives low and the balance between energy gain and loss changes rapidly with very few kilometers of displacement. This is not a map detail. This defines local physics. Variations of only a few % in the incident flux can decide whether the surface is liquid, pasty, or solid. In translation, moving parallel to the edge can be like skating on asphalt that turns into glass and then into sand in a few steps. 3 materials, same rock, different states. The observational history reinforces the image of a system that does not fit a single label. Spitzer had already detected thermal emission and estimated a day side around 2300 K. Webb arrived with more sensitivity and a fuller phase curve, revealing that the dayside brightness varies on separate visits, and that in some bands, the apparent temperature drops below what bare rock would allow. There are sessions that favor a scenario with volatile gases, CO, CO2, exhaled, others that better accept an air dominated by rock vapor, and still occasions where the data are practically flat with no strong signature. Far from being frustration, that is the point. The planet can alternate states, and the terminator is where this alternation is most evident. Why does this belong in our list of frightening places? Because it joins extremes that feed each other. The day provides the raw material, heat and gas, that night immediately tries to sequester. The result is a living edge that does not stabilize. There is no season to wait for. The cold front and the warm front are always touching, with the star pushing from one side and space pulling from the other. If one imagines equipment trying to take measurements there, one can foresee the type of headache: thermal sensors that saturate in the sun and lose signal in the dark, optics that face rapid brightness changes, surfaces that are coatings today and crust tomorrow, dust that is useful condensate 1 hour and bad insulation the next. The risk arises from a permanent edge regime. That doesn't mean everything is chaos. The very constancy of illumination on the day side indicates there must be some repeatable pattern of convection in the magma, cells that are born and die but obey simple forces: gravity, thermal buoyancy, compositional differences in the melt. If the gaseous sheath is indeed tenuous, it should respond more to topography and texture than to organized planetary winds. Grooves can channel hot exhalation into the shadow. Slopes can capture condensates like mineral frost. And if in certain epochs the data favor an atmosphere with CO, CO2, that points to a dynamic balance of interior degassing. More psi in some weeks, less in others. The picture that forms is of a planet with its own time, an internal clock that does not tick exactly with the orbits. Distance helps keep the tone honest. We are inferring from light. Webb measures how this system's brightness changes when the planet passes behind the star, secondary eclipse, and along the orbit's phase curve. These data, when compared to models, make clear the day-night contrast, the variability, and the likely failure of any theory that promises a single solution. In planetary science, that is gold. Each visit becomes an A/B test of the physics we are proposing. Saw a dayside cooler than bare rock would allow? Sign that something is carrying heat away from the subsolar points. Saw the night less cold than expected. Perhaps the gaseous sheath grew or the magma flowed better. Watching the same planet play the same songs on the same instruments is the shortest path to understanding the repertoire. On the mental map, the terminator becomes a belt with various sub-environments. In portions with slopes facing the day, the surface should be near the boundary between liquid and solid. Vitreous skin that cracks and renews, bubbles that pop like spatters and turn into grains as they fly into the shadow. In portions with valleys dipping into night, deposition should beat evaporation. Silicate dust that coats, insulates, and changes albedo, which in turn feed back cooling. Where topography is flat, one can imagine migrating solidification fronts, like mineral frost lines advancing or retreating, with small changes in stellar flux, stellar activity, viewing angle, micro variations in stellar cloud. None of this is gratuitous. It is this kind of process that gives rise to the subtle infrared signatures the instruments detect. Perhaps the most practical question is, what in this chaos is predictable? The orbital period is, the alignment of days with observation windows too. The rest, however, amplitude of the dermal contrast, presence of certain molecules in the gas, efficiency of transport, can vary and has varied. This places 55 Cancri E in a rare category of targets, already characterizable, yet still with room for surprises in every campaign. For a series like ours, which speaks of frightening places for physical reasons and not for jump scares, it is exactly the ideal format, an extreme environment in which risks arise from real, measurable processes, and in which the shock is realizing that the same mechanisms can operate at different intensities from one month to the next. If the previous episode was ice and jets, and before that super dense air and heat, here the theme is the moving boundary between melting and solidifying. It is a trio that dovetails neatly. Venus showed how the sea can be the atmosphere itself. Enceladus showed how fractures breathe with tides. 55 Cancri E shows how a planet can remain forever with one side on and the other off, and how the edge between them is a laboratory in itself. In the next step, it's worth trading the planetary laboratory for a natural radiation accelerator, the neighborhood of a Magnetar. If on rocky worlds, danger comes from what matter does when it heats, cools, or evaporates, near a Magnetar, fear comes from what matter ceases to be when the magnetic field decides to overrule chemical bonds. A Magnetar is a neutron star with a magnetic field so strong, the word strong loses its meaning. Picture a downtown core compressed to the size of an entire metropolis, reduced to a sphere about 20 kilometers in diameter, spinning in seconds and wrapped in a field capable of reorganizing matter, light, and even the vacuum around it. It's not a place of noisy storms. It's a place where the laws we use day to day, chemistry, materials, electronics, simply cease to work. That's why the vicinity of a Magnetar makes the list. There isn't much conversation possible with an environment that switches off the very idea of a stable atom. The first surprise is understanding what an extreme magnetic field actually does. Here on Earth, magnets pull paper clips and motors spin. Near a Magnetar, the field is millions of trillions of times stronger. In that regime, electrons and protons are trapped in spirals so tight that atoms stop being spears with loose electrons and become needles elongated along the direction of the field. Chemistry, this choreography of bonds that gives molecules their personality, comes undone. What we call material loses familiar properties. Hardness, elasticity, conductivity change roles. It's as if the field rewrote, by decree, the operating manual of matter. Next comes the second layer of danger, radiation. Magnetars don't shine like the sun in visible light. They shine strongly in X-rays and, when they hold the finger down, in gamma-ray bursts, capable of saturating detectors at astronomical distances. This brightness is not continuous like a lantern. It pulses with rotation and can fire peaks when the star's crust, a crust of neutrons and crushed nuclei, undergoes stellar earthquakes, starquakes. The field, twisted by spin and internal currents, builds up tension until the magnetic field lines reconnect abruptly, releasing energy in fractions of a second. When that happens, even those far enough away not to feel tides still feel the radiation. Atmospheres are peeled, molecules are broken, electronics turn to confetti. The field itself interacts with anything that conducts current. Wires, circuits, even continuous metallic parts of a structure suffer torques and inductive forces. Moving a piece of conductive in this environment is like dragging a piece of aluminum inside a gigantic magnetic brake. Currents arise that heat, lock, distort, and you don't even need to touch the pure field. Charged particles trapped by it, electrons, positrons, form a light plasma that runs along the lines like beads on threads, emitting radiation as it spirals. To sensors and computers, this feels like storm after storm, with bits flipping for no reason and components heating along paths no terrestrial design anticipates. The star's gravity, in turn, is not there for show. A neutron star has solar mass compressed into a small ball. Even without touching, a hypothetical visitor would suffer tides sufficient to deform long objects, burst internal structures, and of course pull any dust, gas, or debris into complicated trajectories. The magnetic field still imposes order on this process. Instead of falling like free rain, particles are guided by invisible tubes, falling into preferred regions of the magnetic poles. That's why many magnetars are seen as high-energy lighthouses. Radiation comes out channeled like a spotlight sweeping space to the rhythm of rotation. There is also a counterintuitive effect. The vacuum itself changes behavior. In magnetic fields of this magnitude, light is polarized and the vacuum behaves as if it had an embedded glass, a phenomenon called vacuum birefringence. For observers, this complicates measurements. For anyone daring to operate, it would mean lenses and detectors see the world warped in ways we don't encounter in ordinary laboratories. It's one more reminder that near a magnetar, even nothing has an opinion. Operationally, the key word is unfeasible, and that's not drama. Any spacecraft, robot, or instrument needs stable power, predictable materials, electronics that don't go insane. Here, all of that fails at once. Hard radiation multiplies defects in semiconductors. The field makes currents arise where you don't want. Gravity imposes absurd mechanical tolerances, and the very light arrives filtered by a medium that doesn't act like ordinary transparent media. Even before talking about approach, a safe distance calculation already shows that safety and scientific usefulness don't meet. Getting close enough to see details is the same as accepting total loss. But it's not just a story of arrive and die. Magnetodynamics has an almost didactic side about how energy accumulates and is released in the universe. The interior, dense and superconducting, anchors the field as if it were a very well-secured elastic. Rotation twists the lines, the magnetospheric plasma pushes and pulls, and when the tension exceeds the limit, something gives. Magnetic reconnection, particle emission, an X-ray or gamma-ray flash. This cycle resembles in spirit what we see in solar eruptions, only with scales and intensities that turn a sneeze into a detonation. Understanding this isn't mere curiosity. It's learning about the limits of matter and fields under conditions laboratories will never reach. The slow rotation, usually seconds, not milliseconds, creates another feature. Each turn changes the local conditions of the field and the radiation pattern. For a distant observer, it's a regular pulse. For anyone extrapolating what it would be like there, it means the radiation bath comes in waves, with predictable but violent peaks. Predictability, paradoxically, doesn't help. Knowing a peak will come every X seconds gives no time to do anything if the peak itself is incompatible with the presence of any fragile material. It's like timing sledgehammers. The clock's precision doesn't change the fact that the sledgehammer breaks. Another natural question is, at what distances is this already dangerous? The honest answer is, it depends on the event. Day to day, a magnetar's field and radiation destroy the idea of a close neighborhood. In large outbursts, the effects run far. A single burst can, in principle, disturb a planet's ionosphere at enormous distances and cause noise in detectors here on Earth, even with the source thousands of light years away. For the atmosphere of an unprotected, nearby planet, a sequence of surges would be a chemical striptease. Shallow layers of gases leave, complex molecules split, surfaces are sterilized. For electronics even far away, the particle rain is already a difficult conversation. Close by, it's simply the end of the conversation. The magnetar also offers a collection of gotchas of materials. Superconductivity, that elegant property of conducting with no resistance, appears in some internal layers of the star and interacts with the field in ways reminiscent of magnetic pins, locking and unlocking regions of the interior. When those pins jump, rotation gives microjolts, glitches. For those observing at a distance, it's a change of thousandths per second in the spin. For those sketching up-close scenarios, it's a reminder that not even rotation is perfectly smooth. Jolt, reconnection, flash, a chain that repeats the same message. Stability here is always temporary. A comparison with environments we've already discussed is worthwhile. On Titan, risk came from what the place removed. Contrast, heat, clues. On Venus, it came from what the place imposed. Pressure, temperature, chemistry. On Enceladus, it came from ice that breathes through fractures. Near a Magnetar, risk comes from above and below at the same time. From above, from radiation and the field that won't let instruments think. From below, from gravity that pulls everything urgently. Unlike worlds where the solution is to adapt materials and procedures, here the solution is not to go. Study, yes. Approach, no. That doesn't diminish the scientific value of the vicinity. Observations of polarized light test QED to theories. Light curves during flares test reconnection models. Measurements of frequency and its hiccups probe how super-dense matter behaves. Each of these windows has direct utility in astrophysics. It brings together neutron stars, extreme plasma, and the very structure of empty space on a single stage. Fear here is a form of respect. It's accepting that they are regimes in which curiosity operates at a distance. If someone insists on imagining protocols, they would almost be caricatures. No large, free-moving metal, no conventional electronics, nothing that needs chemical stability. What remains in that empty list delivers the essence of the place. A Magnetar is a natural laboratory for extreme physics that does not admit visitors. The only safe position is that of one who observes from afar and translates the signals into models, a job that has been bearing fruit in giving contour to ideas that for decades stayed on paper. In the end, calling the vicinity of a Magnetar frightening is not an exaggeration. It's the rare case in which hostility isn't measured by rugged terrain, bad weather, or aggressive atmosphere, but a combination of field, radiation, and gravity that changes the rules of operation of the material universe. If each destination in our series highlights a kind of limit, this one is the limit of all at once. The place where the atom unlearns to be an atom, light becomes a clue to something we don't see, and any approach plan turns into an exercise in imagination, useful, but strictly theoretical. In the next step, you can take this idea of beamed energy and push it to even larger scales. Leave the fixed beacon of the Magnetar and enter the nozzle of a quasar's relativistic jet. If near the Magnetar, the radiation comes in pulses and flashes, in the jet, it comes like a continuous blowtorch, fed by a black hole that spins, feeds, and spits particles at nearly the speed of light. The logic remains simple. Some places aren't dangerous because they are agitated. They are dangerous because they are too efficient at concentrating energy. A relativistic jet is the blowtorch of a supermassive black hole, magnetized plasma being launched at a huge fraction of the speed of light along the poles of the accretion disk. When that beam points at us, we call the object a blazar. When we see it from the side, it's just a quasar with jets. In both cases, the beam is a narrow corridor of particles, electrons, positrons, and in some models, protons, and magnetic fields where energy is absurdly concentrated. The reason this place makes the list is simple and direct. Inside the jet, radiation and particles arrive in doses that destroy anything in micro-instants, and that holds for many light years from the source. It starts with the bulk flow speed, described by the Lorentz factor gamma, typical values between 10 and 20, sometimes more. This speed compresses the beam's cone into a small opening angle on the order of 1/gamma, and packs energy and light in the direction of motion, so-called beaming. Result: anyone aligned with the beam sees a brightness and particle flux much greater than the normal around the jet. This creates the first useful contradiction for understanding the danger. The jet looks empty, but it's an energized emptiness. Low matter density, yet extremely high energy per particle, and strong magnetic fields controlling trajectories. The radiation comes from two main processes. One is synchrotron, electrons spiraling along magnetic field lines and emitting from radio up to X-rays. The other is inverse Compton. These same particles steal energy from softer photons, from the disk, the broadline region, the dust torus, or the jet's own synchrotron emission, and push them up to gamma rays. In hadronic models, ultra-energetic protons still produce pions, cascades, and neutrinos. The operational verdict is the same in all scenarios. Ionizing doses lethal and instantaneous for any biology, and destructive for electronics and materials. Shielding that would work in reactors and radiation belts does not keep up with the energy scale here. The magnetic field is not just a supporting actor. Near the base of the jet, the flow can be dominated by electromagnetic energy, Poynting flux, which is converted into kinetic energy farther out. Magnetic reconnection, when field lines reconfigure abruptly, and internal shocks, when faster pockets catch up to slower sections, accelerate particles to cosmic energies, and trigger flares that rise and fall in brightness within minutes in our observations. This observed rapidity means compact emitting regions. Translating for anyone trying to imagine operating there, intensity can change by huge factors on a very short timescale with no useful warning. Another piece of the puzzle is interaction with surrounding photons. Near the black hole, there is a sea of light. The accretion disk, the hot corona, the broadline region, and the dust torus. Highly energetic photons from the jet, upon colliding with those slow photons, can produce electron-positron pairs, triggering cascades. Operationally, this is a double wall. On one side, the radiation reaches you. On the other, the very medium creates more charged particles when you thought there was only light. In parallel, the jet's edge has shear with the external medium. Turbulence, instabilities, Kelvin-Helmholtz, mixing of material, nothing that resembles a smooth corridor. Even far from the base, the jet remains hostile. On parsec scales, there is still enough dynamic pressure to strip gas from the path and ablate surfaces. On tens of kiloparsecs, when it hits the intergalactic medium, the jet forms hot spots in radiolobes, gigantic deposits of energy. If that collision, so far from the source, is still capable of heating and inflating bubbles for millions of years, you can imagine what the beam's cross-section does along the way, where energy per area is much higher. Comparisons help calibrate. Jupiter's radiation belts are terrible for electronics. In the jet, you trade many medium energy electrons for few absurd electrons, and you still get hard photons and protons to complete the defeat. A strong solar storm knocks out satellites. Here, the flares are orders of magnitude more energetic, with Doppler boosting reinforcing everything in the beam direction. Thick lead shielding works in reactors. In the jet, piling on mass turns into a target. More material means more targets for secondary reactions, more heating by collisions, more brimstalling. The very clock complicates. Due to beaming and time dilation, the jet's intrinsic variability arrives compressed for an aligned observer, higher, shorter, and more frequent peaks. This destroys any chance of wait for it to stabilize and measure procedures. Also, the beam geometry is not a perfect cylinder. The opening angle can change with distance. We see bright knots, regions where shocks and reconnections are more active, moving apparently superluminally due to projection effects. Translating, neither the track is straight, nor the light is constant, nor the local physics is calm. And there is the engine's origin, which ties everything together, the supermassive black hole and the disk. Magnetic fields anchored in the disk and at the horizon extract rotational energy from the black hole, Blandford Znag-like mechanism, and dump it into the jet. This is efficiency in pure form. Part of the infalling mass enters as fuel, part leaves as a collimated beam. If near the Magnetar the field ruled chemistry, here the field rules the entire hydrodynamics on large volumes. It's the same message on a larger scale, where the field dominates, the habits of materials, mechanics, and electronics cease to apply. Practical question: at what distance is this lethal? It depends on the jet's power. There are blazars whose gamma-ray brightness outshines the entire host galaxy for hours. Around compact emitting regions, any exposed object would see instantaneous radiation doses capable of ionizing surface layers, ripping electrons from materials, heating and breaking bonds, damaging semiconductors irreversibly. Even many light-years ahead, the sum of relativistic particles and hard photons keeps the environment unfit for conventional operations. The trickiest part is that the jet doesn't need to hit you to be a problem. Being in the vicinity already means dealing with deflected particles, scattered light, lateral shocks, and fields that induce currents in any structure. If hypothetically a spacecraft tried to cross the beam's edge, it would find shear, faster center, slower edge, magnetic turbulence, and a shower of particles that would penetrate protective layers, producing secondary radiation inside the very hull. It's engineering in territory with no golden rules inherited from Earth. Why is this both frightening and scientifically valuable? Frightening because it concentrates energy efficiently in one direction. There's no room to stay to the side. Valuable because jets are natural accelerators. They reveal how particles reach cosmic energies, how fields reconnect, how black holes power phenomena visible billions of light-years away. To understand supernovae, cosmic rays, structure formation, jets are key pieces. The price is accepting that the only safe position is outside the beam. In terms of rule of thumb for imagining the environment, if it looks empty, be suspicious. If it stayed stable for minutes, it's because you didn't see the next outburst. If the light is strong, remember it still hasn't told the whole story. You're missing the particles you can't see. If the shielding looks good, recalculate taking secondary radiation into account. And above all, treat distance as a design component. There is no known technology that allows work inside the jet. All learning comes from observing from the side and from afar. Following our trail of extremes, you can take this idea of collimated energy and swap it for an extreme of energy released all at once, the vicinity of a gamma-ray burst, GRB. In a quasar's jet, the torch stays on for a long time. In a GRB, the torch lights for seconds and sweeps space with a single dose that can sterilize worlds light-years away. It's the same family of particle and field physics, only in the pulse version. If a quasar's jet is a blowtorch that stays on a long time, a GRB, gamma-ray burst, is the torch that lights up suddenly, points in a narrow direction, and dumps everything at once. In seconds, it releases more electromagnetic energy than the sun will emit in its entire lifetime, not because it blows up the universe, but because it concentrates and collimates energy into a tight beam. It's short, it's directional, and that's why it's scary. Inside the beam, the dose arrives so fast and so strong that no one has time to do anything. When you notice, it's already over. In practice, there are two main engines for a GRB. Shorts, typically under 2 seconds, come from neutron spar mergers, sometimes accompanied by a kilonova. Longs, from a few seconds to minutes, usually arise from the collapse of a very massive star that forms a black hole with a turbulent accretion disk, the collapsar scenario. In both, the Bayes physics is similar: an extremely compact core, violent magnetic field, and a relativistic jet that exits through the poles with Lorentz factors that can exceed 100, driving electrons and possibly protons at nearly the speed of light. That jet is the cannon. The burst is what we see when it points at us. Geometry makes half the danger. The beam is not a broad lighthouse. It has a small opening angle, something like a few degrees. Within that cone, beaming compresses light and particles in the direction of motion, multiplying intensity for the aligned observer. Outside it, things may even look normal. That's why a GRB is treacherous. The entire universe remains calm around it, but in the aligned swath, the energy per square meter skyrockets. It's not a storm for everyone. It's a corridor of damage, sweeping space, and, if it crosses a planetary system, delivering everything in seconds. What arrives exactly? First, very energetic photons, gamma rays and X-rays, with a spectrum that usually comes from two sources: synchrotron, electrons spiraling in magnetic fields, and inverse Compton, those electrons kicking photons to higher energies. Depending on the event, accelerated protons can initiate cascades of secondary particles. Right after the main crack, the afterglow comes, the jet encountering surrounding gas and generating radiation that steps down in energy, X-rays to ultraviolet, to optical to radio, over hours to weeks. In impact terms, the prompt is the sledgehammer, the afterglow is the vibration that continues. Why is this destructive for a planet? The dose of hard photons ionizes and breaks molecules in the atmosphere and on the surface. On worlds with oxygen, this rapidly destroys ozone and produces nitrogen oxides. The result is exposing the ground to UV for months or years, even after the flash is gone. On worlds without much air, part of the radiation hits the ground directly and cooks surface chemistry. The interval between nothing and dangerous is short. There are studies indicating that effluence of tens to hundreds of joules per meter squared already severely messes up an ozone-dependent biosphere. In plain terms, being close and aligned is terrible. Being at stellar distances, but still in the beam, is still terrible. Being to the side improves things a lot, but does not guarantee peace of mind if you are very close to the source. How close is close? It depends on the event, and they vary greatly. The number that matters is the fluence that reaches your world. A particularly energetic GRB, with a narrow beam and little attenuation along the way, can deliver, in the beam, at a few light years, a fluence that easily exceeds the level that destroys ozone protection. On scales of tens of light years, the effect already drops a lot. There may still be damage, but it's not the total sterilization scenario. That said, there is no comfort in "we got lucky." The statistics of a big universe don't help those in the corridor of the specific event. Another misleading aspect is duration. A flash of 0.5 to 30 seconds seems too quick to matter, except that, for radiative damage, the product is power times time. Compression in time increases instantaneous power. The same energy delivered in less time does more damage to electronics, saturation, single event ionization, and gives atmospheric processes no time to disperse the impact. Think of the difference between standing in strong sunlight for an hour and being in a blowtorch's sights for 5 seconds. The second case is short, but the local effect is devastating. There's also light against light effect. Very energetic photons from the beam can collide with slow photons from the environment, the host galaxy, dust, the afterglow, and produce electron-positron pairs. This feeds cascades that change the medium's transparency and create even more charged particles. For anyone imagining material inside the beam, this means secondary radiation in the inner layers of the very hull. One more reason why stacking shielding doesn't solve it. More material becomes more target for interactions. And it's not just light. In many GRBs, a fraction of the energy leaves as cosmic rays. ultra-energetic charged particles that, depending on magnetic fields along the way, can arrive after the flash in a prolonged tail. For a planet, that adds months to years of extra ionization at the top of the atmosphere. It's less dramatic than the initial pulse, but it contributes to keeping the chemistry off-kilter longer. In the how this happens, the picture is straightforward. In the quasar case, the star's core falls. A black hole, or an extreme neutron star, is born. An accretion disk forms, and along the poles, the magnetic field channels energy outward. The jet carves a path through the star's own envelope, and when it escapes, the GRB appears. In the neutron star merger case, the final dance compresses nuclear matter, arms very strong fields, and fires a short jet. Almost together, we see the kilonova. Optical IR glow from freshly forged radioactive material. In both, the jet is narrow, fast, and irregular, with clumps that can generate substructures in the brightness. From the point of view of those in the beam, this translates into peaks within the peak. The light curve is not smooth. Can you protect yourself? The honest answer is no, if you are close and aligned. By close, understand on the scale of a few light years for powerful events. Not even thick atmospheres hold such a flash without consequences. They hold part, but pay in chemistry. Massive shielding attenuates, but creates secondary radiation problems. Being outside the beam solves 90% of the risk. Increasing distance solves the rest. For detection, the game is the opposite. Be far and have instruments ready. Our constellations of high-energy satellites, like those that alert astronomers when a GRB fires, operate like this. They don't try to stay inside. They only listen from afar and point telescopes at the afterglow. Comparing with the quasar jet helps fix the ideas. In the quasar jet, energy is delivered over a long time. You can imagine walking alongside for light years and still suffering. In the GRB, the window is short, but the peak is enormous. It's the same physical family, relativistic jets, fields, particles, with a different schedule. And that's exactly why this scene deserves to be on the list, because it gives you no warning, no time, and no second chance if you are in line. So far, we have seen energy concentrated in a continuous cannon, the quasar jet, and in a pulse, the GRB. The next step trades energy that goes out for energy that pulls, the region of space in which the very fabric of space-time is dragged by a rotating black hole, the Ergosphere. It's another type of danger. It's not light against you. It's space carrying you along. The Ergosphere is the extra zone of influence of a spinning black hole. It is not yet the event horizon, the point of no return, but it's not normal space either. Between the horizon and a more external surface, the static limit, space-time itself is dragged in the direction of rotation. In that band, there is a simple and annoying rule. Standing still relative to the stars is physically impossible. Anything with mass or light that passes through there is forced to co-rotate. That's what makes the Ergosphere so dangerous. It's not the black hole pulling you like a vacuum cleaner. It's space carrying you along, whether you like it or not. It's worth chaining the physics without mystery. Astrophysical black holes spin. When they spin, they curve space and time in an asymmetric way, generating so-called frame dragging. Outside that vortex, you can still choose your orientation and speed with reasonable propulsion. Cross the static limit, and that choice is gone. All possible trajectories inherit a rotational component in the black hole sense. You can accelerate to go faster, but you cannot zero the spin. If you tried to hover, you would need infinite thrusts. This absence of a fixed position is the first piece of the operational puzzle. The second piece is orbital geometry. Farther out, there are stable circular orbits where a vehicle can live for years. Approaching a spinning black hole, those acceptable orbits move dangerously and abruptly closer to the abyss. The innermost stable circular orbit, ISCO, lies farther in for prograde orbits, same sense as a spin, and farther out for retrograde ones, opposite sense. Result, a small energy error on a retrograde trajectory becomes inimitable infall, long before intuition would suggest. Even in prograde, the margin shrinks. The ergonomics of spacetime reduce your options. The third is energy along the way. Black holes that interest us astronomically are usually feeding hot accretion disk, coronal energetic electrons, sometimes jets. Near the ergosphere, photon and particle densities are high, and hard radiation, X or gamma rays, punishes materials and electronics. Even without touching the horizon, you're already in a high-energy lighthouse, with Comptonized light coming from all sides and magnetized particles cutting through the volume. In parallel, tidal forces rise quickly. The gravity difference between an object's front and back stretches, twists, stresses structures. Nothing breaks cinematically at a distance, but everything works closer to the limit. You can translate these 3 points into practical questions. Why not fly skimming like a probe at Jupiter? Because at Jupiter you still choose orbit and attitude. In the ergosphere, you lose the fundamental freedom not to rotate. What if I compensate with engines? Engines compensate velocity. They don't change the rule of drag. You only trade one rotation for another, with fuel costs that explode when you try to fake immobility. What if I stay to the side without a disk? Even around a clean black hole, the geometric problem remains. Stable orbits are scarce, and small perturbations grow. A curiosity that ties danger and science is the so-called Penrose process, a theoretical way to extract rotational energy using the ergosphere. The trick: an object enters, splits in two. One part falls with negative energy as measured by a distant observer, possible only in there, and the other exits with more energy than it entered. The proof of concept tells us two things. First, the ergosphere has non-intuitive physics, in which energy can be traded with the black hole spin. Second, any high-velocity collision in there can produce extremely energetic products at awkward angles. In the astrophysical version, magnetic fields anchored in the disk extract rotational energy continuously, the Blandford-Zionic-like mechanism, and feed jets, another way of saying the whole neighborhood is energetically charged. If I can't stay, can I at least pass quickly? Passing quickly reduces exposure to radiation from the disk and corona, but worsens other things. At relativistic speeds, a small course deviation becomes many kilometers of air. Any interaction with disk gas, even low density, turns into an abrasive jet. Any maneuver demands lateral thrusts that, so close, convert into orbital energy changes you may not get back. And remember that light itself suffers strong effects. Extreme versions of lensing, aberration, and redshift or blueshift change how sensors see the surroundings, complicating image-guided navigation. Another trap is the psychological limit of "it's not the horizon yet, so there's time." Between the static limits and the horizon, every future points inward to some degree. The mandatory co-rotation can give you the feeling of, "I'm making the turn," but space-time's topology is pushing toward fewer options with every meter. If any part of the trajectory crosses the ISCO, the spiral is destiny. Braking does not give you back a stable orbit. You only fall on a different trajectory to the same end. In engineering, this translates into ridiculous margins, short action windows, high consumption, precise attitude requirements, and a radiative environment that, ironically, shortens the life of the sensors you need to meet those requirements. Comparing with environments we've seen helps fix the why of fear. In the quasar jet and in the GRB, Energy comes from outside towards you, light and particles hitting with abnormal efficiency. In the Ergosphere, the threat is space-time itself. It captures your most basic degree of freedom, not rotating, scrambles your navigation, and places you inside a radiation field coming from the disk and the corona. On Titan, the rule was to read whispers. On Venus, to endure pressure and heat. Here, it's to accept that geometry rules. When geometry rules, propulsion and shielding help little. What would be the safe distance? The answer depends on mass and accretion rate. Far from the static limit, gravity is still strong, but you have stable orbits and a relatively clean sky if the black hole is quiet. Cross the static limit, and the idea of rest is over. Approach the ISCO, and the idea of margin is over. In hungry black holes, even before the static limit, you already deal with radiation fields that make ordinary electronics unviable. In quiescent ones, the pure geometry problem remains. You cannot park, only transit, and a transit that errs a little falls. Why does the Ergosphere then rank among the most frightening places? Because it concentrates three practical impossibilities in a relatively thin region. You can't stop, you can't trust orbits for long, you can't operate sensors comfortably. At the same time, it's a scientifically rich stage. From there come spin signatures, through line profiles and time variations. From there emerge jets we see across galaxies. From there we learn how energy is extracted from pure rotation. The price of seeing up close is far too high. That's why the right strategy is always the same. Observe from afar, infer through models, and respect the imaginary no-entry sign. Continuing along this path of gravity getting the upper hand, the next logical step is to leave the neighborhood of the horizon and look at the orbital cliff that marks the point of no return, even outside the Ergosphere. The innermost stable circular orbit around a stellar black hole. If here you lost the right to stay still, there you lose the right to just one more lap. It's the edge where a minimal amount of energy decides between circling a bit more or plunging. Leaving the Ergosphere and moving a bit farther out, you can point to the exact edge where circular orbits still work, and from there inward simply cease to exist. That's the ISCO, the innermost stable circular orbit. The name sounds too technical to make a list of frightening places, but it's precisely the simplicity that scares. Up to here, one lap after another is possible. Half a step less in energy, and you don't spiral for a little while, you fall. It's an orbital cliff. It's worth fitting the pieces to the right scale. Think of a 10 solar mass stellar black hole. The ISCO, if it isn't spinning, sits about 90 kilometers from the center, 3 times above the event horizon. At that altitude, orbital velocity already hits close to half the speed of light, and a full lap takes milliseconds. What does that mean in practical terms? That trajectory tweaks, readings, decisions, and corrections that in Earth orbit would fit into minutes, here have to happen on the millisecond scale. It's a regime in which the environment's clock overrules any engine. And the stable in the name is honest but treacherous. Stable means that if nothing interferes, you can complete laps. Only near a black hole, nothing stays the same for long. There's radiation from the hot disk, energetic particles in the corona, gravitational kicks from small mass asymmetries in the gas, and the very relativistic effect that warps the surrounding geometry. All of that saps a sliver of orbital energy at every instant. The ISCO, therefore, is not a calm balcony. It's the last handrail before a stairway with no steps. Lose the bare minimum of energy through gas drag, radiation, a poorly timed maneuver, and the circular orbit ceases to exist as an option. There is no go back one square. If the black hole spins, the cliff moves. In the direction of spin, the ISCO comes even closer to the black hole. In the opposite direction, it moves farther out. The friendly part of prograde is that you can get closer and still complete laps. The scary part is that closer in, everything gets worse. Stronger tides, higher speeds, shorter times, harder radiation. Going retrograde gives you breathing room in distance, but charges it back with flimsier stability. You lose the floor sooner. In both cases, the message is the same. This edge is not figurative. On one side there are orbits, on the other there aren't. Radiation near the ISCO in feeding black holes is not decoration. The accretion disk, squeezed by gravity and heated by friction, emits intensely in X-rays. Above it, a corona of energetic electrons hardens that light via Compton scattering. Sensors and materials designed for satellite environments don't last here. Semiconductors accumulate ionization damage, thermal noise and leakage currents blow up, coatings darken or degrade. Even if you don't plunge into the gas, light and particles reach you, scrambling telemetry at the exact point where reading precision is the only thing between one more lap and plunge. Another detail that becomes an obstacle, what we call atmospheric drag in low Earth orbit, shows up here in almost caricature form. The disk isn't air, but it is gas, and even a wisp of density at relativistic speeds bleeds orbital energy at a rate that can't be ignored. The difference of being 2% more immersed in the gas can be the difference between having enough thrust to maintain orbit for a few dozen laps or being pulled into a spiral in a matter of seconds. Near the ISCO, 2% isn't a detail, it's a diagnosis. Tides complete the trap. The gravity difference between front and back or between the sides of any structure grows absurdly fast as the radius shrinks. They twist, stretch, and test every joint in every axis. For a human body, the conversation doesn't even start. For a robotic structure, it starts and ends with tolerances that look viable on paper, but in the real environment, hit the combo of tide plus radiation plus short times. If one part of the vehicle goes a centimeter farther into the disk than another, the differential in drag and heating already changes and begins a sequence of small asymmetries that feed orbital loss. It's a place where perfect isn't hubris, it's a requirement. Visual navigation, which saves us so often elsewhere, goes into crisis here for relativistic reasons. Light come off from behind is pulled, what goes ahead is pushed. The color shifts, red shift, blue shift. Relativistic aberration compresses the world in the direction of motion. Lensing curves paths in ways that fool any algorithm trained on Newtonian images. You look, you recognize patterns, and the patterns no longer mean what they meant. Again, the edge doesn't forgive. You must fly by instruments that are themselves being attacked by radiation, and do so on the timescale of a few laps per millisecond. And if we use brute force, the question is natural. At the ISCO, burning fuel to hold the orbit is like hitting the brakes on ice. It works until physics says there's no more friction for you to buy. You can compensate small losses for some time, but the cost rises exponentially as you try to pretend you're in a regime that's already over. When the circular orbit ceases to exist, adding thrust only changes the shape of the fall. The why this is interesting walks alongside the why this is dangerous. The ISCO's position, measured indirectly by the disk's light, is a ruler for black hole spin. The closer it sits, the larger the spin tends to be. The X-ray spectrum, the shape of distorted iron lines, the timing of quasi-periodicities show how matter behaves at this limit. Its strong gravity physics in a natural laboratory no particle ring can replicate, but the lab doesn't accept people nearby. All useful information comes from watching at a distance and modeling. In the imagination, the the ISCO seduces because it seems like a line you could draw on the map. From here inward, it's over. In practice, it's an interval of no return sharpened by real processes, drag in the gas, radiative losses, tides, radiation, and timed by clocks that shorten as you approach. It's a place where small inaccuracies turn into quick consequences. And that's why it's on the list, because almost doesn't exist here. You don't almost stay, you almost fall, and fall. Keeping the series sequence, you can leave this gravity cliff and trade sudden drop for organized chaos on planetary scales, staying closer to home. Saturn's F-ring. It's the opposite in aesthetics, bright, thin, photogenic, but the risk logic is related. Tiny margins, frequent perturbations, and an environment that looks calm until you discover stability there is the exception, not the rule. The F-ring is that thin, bright line just outside the A-ring that shows up in almost every classic picture of Saturn. From afar, it looks like a delicate stroke in the shepherd moon's brush. Up close, it's a zone of collisions, gravitational tugs, and structures that appear and vanish so fast that an image taken now already contradicts tomorrow's. The reason it makes the list is straightforward. It's a place where everything is narrow, width, margins, tolerances, and at the same time, nothing stays still. The result is an environment lovely to look at and complicated to operate in, where predictions die in practice because the ring itself keeps changing its face. Geometry helps explain the F-ring's nervous character. It sits just beyond the outer edge of the A-ring and is held in place by two small moons, Prometheus on the inside and Pandora on the outside. These two shepherds aren't gentle guardians. They are near-miss tugs, one on each side, constantly messing with the ring's profile. The F's core is narrow, tens of kilometers, but around it there's a fringe of dust, strands, and filaments that extend radially for hundreds of kilometers. The ensemble resembles a thin rope surrounded by frays, and, now and then, by knots. The key point, what gives the ring its shape, isn't a solid edge, but a dynamic balance of gravity, collisions, and orbital shear. That shear is the first physical piece worth fixing in mind. In Kepler's orbits, whoever is a little closer to the planet rotates a little faster. Whoever is a little farther, a little slower. In the F-ring, a little means meters to kilometers. Tiny differences that multiplied over hours and days stretch any perturbation into long threads. An ice grain that hits the core and exits, displaced outward, will fall behind in longitude. Another that moves a bit inward advances and meets new particles. That's how filaments, spirals, and radial plumes are born. It's not confetti. It's the visible signature of small orbital differences turning into big structures. The second piece is the shepherd moons. Prometheus, the inner one, has a particularly striking effect because it periodically passes very close to the ring, pulling material from the core and opening furrows, narrow channels that shear later stretches into long tendons. Each passage creates a pattern, and these patterns overlay. Pandora on the outside pulls the opposite way. It holds and wrinkles the outer edge. In sum, the core gets punched now inward, now outward, while the peripheral frays gain and lose prominence. It's common to say the moons maintain the ring. More precise is to say they make possible a ring that exists only because it is being pinched all the time. The third ingredient is the ring's self-gravity. In some stretches, the core concentrates enough mass to gather particles into transient clumps, hundreds of meters to a few kilometers, made of porous ice. Some survive several laps. Many become just a kernel that breaks apart after a brush with the core or with Prometheus's tug. These kernels are responsible for features nicknamed mini-jets, narrow fans of material ejected radially, when a clump grazes the central strand. The jet is born in minutes, grows to tens or hundreds of kilometers, and then fades, stretched by shear. Anyone who tries to map the ring as if it were a road quickly discovers that the layout has a life of its own. All this happens in a granular medium, ice ranging from fine dust to blocks as big as rocks, occasionally with larger clumps. Collisions are frequent and most of the time low speed, centimeters to a few meters per second, but in orbit, that's enough to heat, break, stick, and launch. Grains coated with ice frost have friction and reflection properties that change with each hit. In one and the same stretch, local density can triple or drop by half in a few hours, simply because a kernel passed, hit, splashed material, and was shredded soon after. The ring is thin in total width, but thick in events per minute. One deceitful detail is brightness. The F-ring can look uniformly bright in one photo, and in another be full of shadows and dark lines. This effect isn't just a camera magic trick. The appearance depends strongly on the lighting angle and on the angle from which the observer sees the plane. In shallow geometries, fine grains forward scattered lots of light, and what was nothing becomes visible. In backlit geometries, the core may look darker than the fringe. At Saturn's equinox, with the sun level with the ring plane, long shadows and vertical structures pop out that almost don't appear the rest of the year. It's not just aesthetics. Light orientation changes which features dominate the reading, and, consequently, conclusions about density, grain size, and activity. Electricity enters the story by a subtle path. Fine dust grains charge easily in Saturn's magnetospheric plasma. Small charges on small grains suffice for electromagnetic forces to start competing with local gravity and radiation pressure. The result is trajectory deflections and changes in height, latitude, for particles that, from a purely gravitational point of view, should stay glued to the plane. These excursions create braided features and small undulations off the main plane, almost invisible at many angles and very clear at others. Just change the lighting for a braid to seem to have appeared out of nowhere. The F-ring's recurring lesson repeats. What looks like absence may just be poorly lit. The plasma environment and the presence of micrometeoroids complete the catalog of annoyances. Meteoroids that cross the ring at high speeds vaporize part of the material and create instantaneous sprays. Fragments recaptured by the core alter local compositions and grain size distributions. In parallel, tiny differences in the electron density around the ring change how radio signals are dispersed and how the particles themselves charge, which feeds back into the filament pattern. The ensemble looks like an orchestra of many instruments playing short passages at the same time. If the question is it stable? The honest answer is, as a system, yes. As a feature, no. The F-ring has existed for a long time and remains there because the statistical balance between tugs, collisions, and losses holds. But the point-by-point shape, the jet here, the fold there, the channel yonder, changes on a cadence that escapes any routine that confuses ring with fixed ring. With every set of orbits, Prometheus comes back to sculpt. With every camera resolution, new mini-jets are seen. With every season, lighting reveals surprises. Making a map of the F-ring is recording a chapter, not closing the book. This has clear practical implications. Crossing the ring plane near F is not like passing through a homogeneous veil of dust. It is entering a volume where pieces the size of balls, blocks, and clumps may be exactly in the wrong place at the wrong time. The low average density is misleading. The danger isn't in the average, it's in the point-like. Radar and optical detection struggle because much of what matters is the right size to confuse the return, Moreover, relative motion is high, and velocity profiles very little with radial position, which robs some methods of Doppler contrast. A clean flight plan on the eve can be obstructed hours later by a newly formed jet. Comparisons help calibrate without exaggeration. The B ring is massive and bright, but predictable over larger time blocks. The D ring has dust, but is diffuse. The E ring is more of an extensive halo fed by Enceladus. The F is low mass and highly active, precisely the kind of combination that produces hour-size phenomena. Difficult and relevant for materials and sensors. That's why, scientifically, it's valuable. It serves as a test bench for disk dynamics. The Shepherd-Ring interaction recalls gap formation in protoplanetary disks. The transient clumps resemble growth attempts that fail and repeat. The jets are analogs of collisional events in thin media. Understanding F imports intuitions to much larger scales, with the advantage that here, you can watch the whole movie several times in the same year. The ring's clock, by the way, is friendly for those who study and hostile for those who plan to cross. In hours and days, you can watch structures be born and die. In weeks, patterns reorganize. In months, lighting changes and shows another layer of the same physics. For a mission, that means short-term predictions are useful, but medium-term guarantees are unlikely. A mosaic made today still holds tomorrow. In a month, it's already memory. The ring forces you to design with margin and to respect the idea that in a medium like this, unprecedented is routine. One curiosity that ties it all together: the F-ring feeds and loses itself at the same time. Prometheus drags material out of the core, but part of that material returns, falls back, compacts, or becomes fray that dissolves. New clumps are born of what remained of old ones. Some grow enough to earn nicknames of quasi-moons, and then, at the first bad encounter, become jet and dust. On long scales, what you see is a cycle of trial and error in which gravity tries to assemble and shear tears down. The ring exists only because it is always under construction and demolition at the same time. Why is all this scary in the key of our series? Because it's an environment that sells itself as a thin line and delivers an incident factory. It looks simple, it's complex. It looks clean, it's full of hot spots. It looks stable, it's always recalculating. And above all, because everything happens on small margins. Displacements of tens of meters in the Shepherd Moon's position, something that sounds irrelevant, change the channel's design. Clumps the size of a building, which sound tiny on a planetary scale, generate structures hundreds of kilometers long, visible from the other side of the system. It's a place where a little often produces a lot. Now it's worth trading the F-ring's incident factory for a terrain-trapped factory in microgravity, active pits, walls that collapse slowly, dust jets that change the landscape with the sun. In other words, leave the thin ice thread and go to a porous nucleus with mouths that open and close, like on Comet 67P, Churyumov Gerasimenko. There, energy is scarce, but the terrain does the job. A miniature version of the F's risk, the small error that becomes big, appears with the aggravating factor that a wrong step doesn't give free fall, it gives a slow, irrecoverable fall. The nucleus of 67P has the famous rubber duck shape, two lobes linked by a narrow neck. Just a few kilometers end to end, and with infinitesimal gravity, it seems harmless until you closely follow what happens around the active pits. These almost circular cavities, with crumbly rims and steep walls, act like the mouths of a breathing underground system. As the comet approaches the sun, heat penetrates a bit into the porous material. Water ice, carbon dioxide, and carbon monoxide begin to sublimate at depth. The gas seeks a way out. The roof, supported by a dusty crust, loses support and collapses. The result is a space sinkhole, a fresh collapse crater with stratified walls and jets that fire like aerosols, launching dust and ice grains hundreds, sometimes thousands of meters above the rim. Microgravity is the first real complicating factor. On 67P, gravitational acceleration is tens of thousands of times smaller than Earth's, and the escape velocity is on the order of 1 meter per second. That turns physics upside down. A little stone that detaches from a rim doesn't fall like a stone. It floats in a lazy arc, sometimes bouncing and leaving visible tracks in the dust. A puff of gas that on planet would only lift dust off the ground here rips out particles the size of balls and throws them far away. At the same time, any attempt to contact the terrain risks being met with a kick. You push the ground pushes back, and you take off unintentionally. That's why the Philae lander bounced twice before stopping. The harpoons failed, the reaction from contact was enough to expel it, and on 67P, to jump isn't a figure of speech, it's orbital mechanics. The pits themselves are a catalog of processes gathered at the same address. Many have stepped walls, with layers a few meters thick that betray layered construction. Packages of ice and dust deposited at different times, each with its own porosity, texture, and strength. In some, you can see slightly lighter coloring on internal slabs, exposed ice that has just lost its dust cover. The clock there ticks on two scales at once, that of minutes when a jet switches on with the local sunrise and off at sunset, and that of weeks to months when rims retreat, roofs cave, blocks fall, and the entire crater grows a bit. That sunrise and sunset deserve a pause. 67P rotates in about 12 hours. Each morning quickly heats the comet's skin. The material has low thermal inertia, heats and cools easily. In the dark, vapor that failed to escape can recondense in the interior. The next morning, the heat front finds fresh ice in microcavities and produces a sudden gas expansion. The jet cuts the wall, and another piece collapses. This repetitive mechanism creates daily cycles of activity, stronger jets at certain hours, weaker at others, and seasonal cycles, near perihelion. When the comet is closer to the sun, everything becomes more intense. It's not just pretty in the images, it's the engine of a chain of risks that are predictable in general and unpredictable in detail. Risk on 67P rarely appears as one large isolated event. It arises as the sum of small effects. Dust that falls slowly and clogs radiators, grains that stick to lenses and send a camera's contrast plummeting, electrification of particles that cling to surfaces because of the solar plasma and ultraviolet light. The same dust that, seen against the sun, draws magical columns, seen from the wrong side becomes noise for navigation, including for star trackers, which can mistake reflections for stars and misread attitude. And if charge accumulates on a panel or structure, thanks to asymmetrical deposition of charged particles, the discharge sparks are small, but enough to flip a bit at the moments when instruments most need calm. The pit walls aren't rock, they're weak mixtures of ice and dust, with cohesion on the order of tens to a few hundred pascals. That's nothing in engineering terms. A human pushing with a hand would cause damage, but a machine with mass of tens of kilograms on contact reshapes things. But microgravity plays the contradiction. Since the effective weight is tiny, touching without digging is physically possible. It's the part of the problem that invites boldness, except that any expelled thrust, a thruster gas for example, can blow on the rim and trigger a mini avalanche that topples the very support platform. In simple terms, the ground allows contact, but doesn't tolerate puffs, nor knocks, nor vibrations for long. The jets are another source of surprises. They don't come out as perfect columns. They come out as narrow, multiple beams, with intensity and direction varying as the geometry of the fissure down below changes. When two or more beams cross, shear pulls larger grains from the rim, ejecting sprays that last minutes. On busy days, a pit can emit jets that switch on and off with rotation, making stroboscopy in the comet's sky. That affects any operation around because it introduces unpredictable non-gravitational forces, the push of gas and the impact of particles on an antenna, an arm, a shroud. With escape velocity so low, even a weak puff creates acceleration that the spacecraft or any structure feels. And there's also the fallback of what doesn't escape. Part of the dust and ejected brains fail to gain enough speed and return to the nucleus in a slow snowfall that selects deposition areas, gentle depressions, the neck, the base of walls facing shadow. 67P shows smooth mantles in contrast with rough slopes, exactly where the debris fall finds geometric traps to settle. These fine dust pavements, centimeters to decimeters thick, hide ice under the skin. They look firm until they give way like flour mixed with care. Can you walk there? In Earth mechanics, perhaps, on 67P, walking is a sequence of pushes that launch you upward. The safe thing is to anchor, and anchoring here is a complicated verb. The chemical environment adds its own seasoning. Rosetta's spectrometers showed that the comet is an organic mixture with ice. Methanol, formaldehyde, ammonia, hydrogen sulfide, traces that yield headlines like "smell of rotten egg and horse" when translated to human smell. This matters because different compositions sublimate at different temperatures. A pit richer in CO2 reacts early with cold jets that strip dust before water begins to take part. Another, richer in H2O, looks calm until the sun hits harder. The mosaic of active pits is, then, also a mosaic of chemistry, and that shifts the peak activity times from one sector to another as the season advances. The nucleus's rotation isn't left out. The jets don't just respond to rotation, they change the rotation. Each ejected plume imparts a tiny torque. Summed over weeks, these torques adjust the comet's period by minutes. In practice, 67P's internal clock slips a bit each season. That messes with fine prediction of shadows, local sunrises and sunsets, the raw material for anticipating activity peaks in each pit. An observation schedule planned based on yesterday's period can arrive slightly out of phase tomorrow. In comfortable environments, a minute is nothing. Here, a minute changes the entire show. For terrain lovers, 67P still offers cliffs and walls with spectacular slow-motion instabilities. There have been events in which an entire cliff collapsed, generating an unforgettable flash and plume, followed by a carpet of fresh debris at the base. The mechanism is simple: undermining from below. Sublimation gnaws at the base of the wall. A slab loses support and topples. The timing with lit hours, the coincidence with local maxima of solar flux, and the appearance of bright material soon after, exposed ice, tie the explanation together. The operational message is transparent. Slopes are silent enemies. In microgravity, the fall isn't thunderous. It's enough to redecorate the neighborhood and bury sensors. The next topography, the Hopi region, dark and apparently smooth, is a chapter of its own because it channels jets. The geometric bottleneck concentrates flows and creates gas winds that sweep dust, generating surface undulations that resemble dunes. They aren't aeolian dunes in the terrestrial sense. They're bed forms sculpted by rarefied gas pushing light grains in ridiculous gravity. Still, the practical effect is the same. Tracks that change, crests that migrate, marks that confuse a naive reading of a trail. A map made in 1 week is already out of date the next. Even the lighting complicates things in a way that doesn't appear in pretty renderings. In certain geometries, the grazing sun produces shadows that exaggerate relief and make a hole look like an abyss. In others, washed light removes the wall's relief and hides steps that matter for support. In real missions, that scrambles machine vision. Algorithms trained for lunar or Martian craters with strong shadows, high contrast, and a stable horizon skid on 67p. The solution is to combine inertial telemetry with active sensors, LiDAR, proximity radar, and accept that the camera is, many times, the third opinion, not the first. None of this diminishes 67p's merit as a laboratory. Quite the opposite. The pits show live how gases escape a porous body and how the surface collapses when support vanishes. The layers reveal a history of accretion and reprocessing. The returning dust paints the map of material circulation. The jet's torques quantify how small pushes reprogram spins. The science here is first-rate. It explains everything from other comets' morphology to bigger problems of slope stability on small bodies and grain transport in infinitesimal gravities. And as a bonus, everything happens on human timescales, hours, days, months, not centuries. The frightening label fits because microgravity doesn't forgive naivete. On 67p, falling doesn't kill by speed, it kills by irreversibility. Slipping on a gentle slope means losing contact with the ground and entering a slow parabola that carries you away from the safe spot. And nothing in your body or vehicle has enough weight to brake by friction. A small wrong thrust throws you above the ridge. A jet that switches on at the wrong moment spins you. The dust that seemed like decoration becomes instrument blinder. In other words, the environment doesn't help at all. From that comes the practical rule that ties the whole chapter together. Do everything gently, do everything with redundancy, and expect variation. Small pushes, multiple anchors, cross-checked readings, schedules that follow not only the sun, but also each pit's mood. And above all, patience to accept that map on a comet is a verb. You map what is now. Tomorrow there's another rim, another step, another jet, and it's precisely that plasticity that makes 67p fascinating to study and uncomfortable to operate. Following our trail, we now leave microgravity full of jets for a giant gravity bathed in radiation, the neighborhood of Jupiter's radiation belts. If here the risks came from rising dust and yielding rims, there they come from electronics losing their minds, atoms arriving uninvited, and fields that pass through the hole as if it were a curtain. It's swapping terrain instability for invisible hostility, with the same central message: the small error added up gives no second chance. If Saturn's rings mislead with beauty, Jupiter's radiation belts mislead with the appearance of a clear sky. There is no dramatic dust cloud or visible tongues of flame. There is a gigantic magnetic field, spinning fast, that traps and accelerates particles to insane energies. The result is an apparently empty volume that treats matter as a target: atoms, plastics, solder joints, sensors, and bits. That's why this region deserves a place among the most frightening environments in the solar system. It doesn't knock you down with wind, heat, or gravity, but with invisible particles and hard photons that pass through holes and change the behavior of everything that depends on stable electronics and chemistry. The story begins with 3 simple ingredients that together become a radiation furnace. A huge planet with fast rotation, about 10 hours, a strong magnetic field, and a constant plasma source. Rotation injects energy into the system like an engine that's always on. The field creates traps for charged particles, and the plasma comes mainly from Io, the volcanic moon. Io's sulfur dioxide plumes turn into ionized gas, which forms a torus around the moon's orbit. From that reservoir, currents and electromagnetic waves push ions and electrons inward, where, by conservation of adiabatic invariance, they grow more energetic as the radius shrinks. It's like pushing skaters toward the center. Without touching, you've already increased the speed, and a lot. Within this immense field, electrons reach mega-electron-volt energies, and protons go beyond, with a population of heavy ions, sulfur, oxygen, from the same nursery at Io. These particles aren't stationary, they drift, spiral and bounce along the field lines, gain additional acceleration from reconnections and from chorus and hiss-type waves that sound like music on a plasma radio. For us, the consequence is prosaic: dose. In a few grazing passes through the belt, a set of circuits without proper shielding accumulates a total ionizing dose capable of altering transistors' electrical parameters, darkening coatings, creating leakage currents, and shifting memory thresholds. In design language, it's the moment when specification becomes lottery. What makes Jupiter particularly treacherous is that the radiation doesn't come from a single well-behaved shell. The environment is stratified and variable. There are inner zones with ultra-high energy electrons, capable of traversing millimeters of aluminum and nesting in dielectrics, where they sit for hours or days until they trigger an internal discharge, the notorious deep dielectric charging. There are regions where ions dominate, and the damage is more from atomic displacement in materials, degrading sensors, darkening optics, and there are corridors where plasma waves momentarily sweep electrons outward, only to repopulate them with a new accelerated batch. The map exists, but it looks like a traffic map, good for trends, bad in the details. The planet's rotation introduces another complication. Jupiter's inner magnetosphere co-rotates with the planet, trying to drag the plasma at the same angular speed as the atmosphere. That electric drag force imposes fields that accelerate and break particle populations, and anything immersed in this bath sees different potential environments across parts of its own structure. That's how differential charging arises on surfaces. Panels, edges, and shadows accumulate different potentials. When the difference passes the limit, small discharge sparks occur that confuse sensors and sometimes burn paths in circuits. What would be an electrostatic flick here on Earth in Jupiter orbit triggers equipment resets. On the visible side of the phenomenon, the very existence of synchrotron radio emission is a reminder of scale. Relativistic electrons spiraling in the planet's field emit strongly in radio, to the point that we can see the belts from Earth with radio telescopes. Where there's synchrotron, there are MeV electrons. Where there are these electrons, there's danger for materials and semiconductors. Farther in, that same population produces brumstrelling, hard photons generated when electrons break, passing near nuclei, adding a bath of X-rays that doesn't need a direct line of sight to be bothersome. Shielding doesn't make the problem disappear, it changes its nature. Part of the energy turns into secondary radiation inside the hull itself. The belt's geometry worsens or improves, depending on the path. Near the magnetic equator are the highest and most persistent doses. At the poles, the field's topology opens a path for precipitation into auroras and for less populated corridors between encounters. Missions like Juno chose highly elliptical trajectories, diving over the poles and crossing the inner region quickly to spend less time where the bath is strongest. This strategy makes it clear that here, distance and time are the only reliable dampers. The deeper and the longer, the worse. Jupiter isn't just radiation, it's also plasma and dust. The tenuous ring system and the rain of micrometeoroids create a population of charged grains that, as they dive through the belts, behave like electric dust. These grains can collide with surfaces at enormous speeds. The local orbital speed is high, eroding layers, darkening windows and releasing even more material into the environment, which returns charged. In the lab, it's hard to reproduce the combo grain plus charge plus energy plus plasma. At Jupiter, it's routine. The Galilean satellites add texture to this picture. Io injects material and, with its torus, defines a marker of the medium. Europa and Ganymede suffer sputtering. Belt particles knock atoms off icy surfaces, creating tenuous atmospheres and leaving chemical signature that change with exposure. Ganymede, with its own mini-magnetic field, draws a bubble within the bubble, diverting part of the flux and concentrating another part in specific regions. For anyone imagining operations, this means that radiative sun and shadow zones follow not only latitude, they also follow the relationship with the moons and with the magnetosphere. Each one reshapes around itself. The sun, even at 5 AU, doesn't stay out. Solar wind shocks and compressions tighten and loosen Jupiter's magnetosphere, shifting boundaries and changing particle fluxes in minutes to hours. These events move the environment's baseline. What was acceptable yesterday becomes critical, with no visible change in the landscape. The closest parallel in spirit is Earth's South Atlantic anomaly, which scares satellite operators with higher than expected doses in a geographic region. At Jupiter, the anomaly is the entire planet, with regions that rise and fall in mood as the solar wind decides. Engineering learns quickly with this kind of environment, but pays in mass, cost, and operating restrictions. Electronics boards need tolerance to total ionizing dose, TID, resilience to single events, SEU, SEL, and designs that limit internal charging. That translates to chips on thicker processes, triple redundant logic with bit voting, internal conductive layers to drain charges, and watchdog routines that reinitialize systems when a bit flips. The structure gets metal vaults to attenuate flex. Windows and optics receive materials that resist radiation darkening. Antennas and panels are designed to minimize floating edges that accumulate potential. All of that works until the environment steps up a notch. The reason for respect remains. Jupiter's belts operate orders of magnitude above what we learn to treat as hard. There's a little discussed aspect, important for navigation. Noise. Star tracker, fiber optic gyroscope, photon counting, CCD, CMOS, anything that depends on measuring small signals over a predictable background suffers when the background is peppered with particles. Ghost stars appear. False events saturate pixels. Gain maps change over time due to cumulative darkening. The result is that right when the mission needs clean telemetry to cross a difficult region, the vehicle's own eyes become less reliable. The solution is redundancy in cross-checking among instruments. Let the inertial system distrust the tracker, the radio distrust the inertial system. Attitude be confirmed by multiple measurements. In a place where particles like to flip bits, the policy is to distrust every critical bit. The physics that accelerates and redistributes particles also sets up surprises. Interchange instabilities, magnetic relatives of the old Rayleigh-Taylor, allow blobs of denser plasma to slide outward while lighter plasma slips inward. For a mission, this means gradients that change without warning, with blobs of heavy ions where you were expecting electrons, and vice versa. Meanwhile, co-rotating waves that pervade the magnetosphere modulate the precipitation rate into auroras. And strong aurora on Jupiter is synonymous with closed particle circuits that also pass the regions where vehicles want to fly. None of this runs outside known physics. It runs at the limit of the physics we know. Frightening here has a different tone. It's not the ground giving way, nor heat softening structure. It's the environment's ability to invade matter and information. A solder joint withstands push and vibration, but not atoms being displaced from place by repeated submicroscopic impacts. A control algorithm withstands air turbulence, but not a gyro counter that resets itself because a relativistic electron crossed the wrong logic node. A solar panel withstands dust. It doesn't withstand a year of ions crossing the mesh and killing production through cumulative damage. Even so, the belt's neighborhood is scientifically precious. It explains how fields and waves accelerate particles in astrophysical environments, serves as a laboratory analog for jets and shocks on larger scales, and reveals how moons and magnetospheres converse. The radio we detect from Earth mapped high-energy electrons. The ultraviolet and X-ray auroras tell where and how particles precipitate. And real-time variations show coupling with the solar wind. All of that becomes useful physics for other planets, for the Sun, and even for the galaxy. If the sequence of destinations has made sense so far, we can keep pulling the thread by leaving this invisible storm for a place where the danger becomes tangible again, but with the same DNA of small errors turning into big problems. Sloped faces of Rubble-pile asteroids, where gravity is ridiculous. Friction deceives and the terrain answers with avalanches that seem slow, but give no respite. It's the pocket version of instability, less energy per particle, more chance of slipping for good. After leaving Jupiter's radiation belt's invisible storm, we land, unintended pun, on a much more tangible kind of danger, terrain that looks firm and isn't. Rubble-pile asteroids are small bodies spinning fast, made of loose aggregates of rocks, gravel, and dust, held together by weak gravity and a bit of grain-to-grain cohesion. The mental image of a quarry levitating isn't far off. Car-sized blocks coexist with pebbles and fine dust, all accommodated in a porous structure, with voids, cracks, and improbable cliffs. What puts them on this list isn't just the rugged aesthetics, it's the combination of unstable slopes, ridiculous gravity, and rotation that changes the rules of the game. A perfect tripod for turning any misstep into a chain of problems. It starts with gravity. On many of these asteroids, acceleration is so small that escape velocity is on the order of tens of centimeters to a few meters per second. In practice, to jump stops being a figure of speech. A little shove can take you off the ground and not give you back. That makes any interaction with the terrain delicate. The weight is tiny, so simple contact doesn't compact the soil as on Earth. On the other hand, the slightest gas puff, a mechanism's jet or a touch that's a bit too firm turns into a launch. That's how touching a slope becomes a high-precision maneuver. The friction that normally saves the skid hardly exists, and inertia overrules your will. The second piece is the very nature of the soil. The filling of these slopes is granular, grains of varied sizes, with friction, weak cohesion, and collective behavior that escapes our daily experience. The dominant physics is of the Moore-Coulomb family, a balance between friction and cohesion. Only the cohesion, even small, matters a lot when gravity is minuscule. Forces that on Earth would be negligible, like van der Waals between grains, start holding little clumps and allowing small overhangs. Result, inclines that to the eye seem too steep to stand can indeed stand until something vibrates, heats, cools, or hits. The boundary between stopped and slid is narrow, and the decider is the detail. Rotation ties it all together. Many rubble piles are top shapes, more bulged at the equator, like spinning tops. The reason is simple. Centrifugal force softens effective gravity at low latitudes and pushes material toward the equator. Over thousands of rotations, pebbles migrate, slopes ooze, crests grow, and depressions fill. Small changes in the rotation rate, for example, from the Oort effect, in which sunlight and re-emitted heat give minuscule but cumulative torques, shift the boundary between stable and on the verge of sliding. An asteroid that today holds its rim may, sometime from now, lose some material to the equator without any earthquake, just because the spin clock was adjusted by light. That ooze isn't the roaring cinematic avalanche. It's a slow-motion flow. Grains slide, make little hops, saltation, rearrange neighbors, create micro-steps, stop. Frequent interruptions due to the relief generate catches and locks. A pebble holds others until at distant impact. A millennial pebble throw shakes everything and frees the group. This sensitivity to vibrations has a name in granular engineering, but here you can call it daily reality. Each micro-impact the asteroid suffers, and they suffer many, turns into a shake that readjusts entire slopes by millimeters to centimeters. Over years, the millimeters become meters. Heat enters from another flank. The day-night cycle on an asteroid is short. Surfaces heat in the sun and cool quickly in shadow because thermal inertia is low. This back and forth cracks rocks, thermofracture, generates fine debris, and tweaks the cohesion of the near-surface granulate, freeing grains that slip downslope when the local angle passes the acceptable. In the limit, slopes acquire that exfoliated look, with faceted stones and boulders resting in uncomfortable equilibrium. The little ponds of fine regolith, so-called ponds, form exactly where flows stop, closed basins and low potential zones, often near the equator. They look inviting, but can be traps, soft surface, little anchoring, and cohesion that, if it exists thanks to grains stuck by weak forces, easy to undo. A silent complicating factor is static electricity. Sunlit grains emit electrons. Grains in shadow receive electrons from the solar wind plasma. Near the terminator, the line between day and night, weak electric fields can levitate light dust by centimeters to meters. It's a little thing, but in minimal gravity, it's enough to keep dust layers moving, cleaning some surfaces and dirtying others. For optical sensors, that becomes noise. For surfaces that need to stay clean, windows, radiators, contacts, it becomes maintenance no one wants to do in the worst possible place. Visually, Rubble-pile slopes pull two tricks that train patience. First, scale. Without trees, without reliable horizons, and with hard shadows, a 30-centimeter stone can look like a 3-meter rock, and vice versa. Second, contrast. Sun angles near the horizon cast long shadows that exaggerate steps. High sun flattens the relief and hides traps. Vision algorithms trained on the Moon and Mars, environments with higher gravity, more well-behaved shadows, and more continuous landscapes, tend to err here. Recent missions learned the hard way not to trust smooth seen from afar. Smooth can be loose, fine gravel over void. But why is this dangerous to operate in? Because everything we expect to help doesn't help. Wheels need weight to generate traction. Here they don't have it. Legs need friction to bite. Here they slip. Anchors need terrain reaction. Here the terrain gives way. Harpoons call for kickback to set. Here the kickback is launching you. Even a simple gas puff for cleaning or maneuvering creates its own problem. It lifts the cloud of grains and pebbles that scrambles sensors, dirties everything, and can return as a slow rain, hitting where you least want it. Shock absorbers that on Earth swallow energy, here return it as a hop. The physics gives no pardon. Another gotcha is the extreme homogeneity. In a few meters, the slope can change from compact block to gravel, from gravel to cohesive dust, from dust to nothing supported on 3 pebbles. This mosaic is tied to the asteroid's history, how many impacts it took, how the material redistributed, what rotation it had when it formed its current shape. On asteroids where material migrated a lot to the equator, the belt can be a thick deposit of gravel. Higher latitudes show rockier slopes, with overhangs and cliff faces that look impossible, but are there, supported by jammed blocks and the little cohesion among fine grains. Collective effects appear that only exist in this regime. Imagine a sofa-sized block resting on 2 watermelon-sized stones. In normal gravity, that's unstable. Here, it can last years. Now imagine a micro-impact kilometers away, shaking the slope by micrometers. 1 watermelon turns, the sofa drops millimeters, pushes a neighbor which rolls a few centimeters, which knocks another watermelon which, there, a chain of instabilities that becomes a tiny grain avalanche down the slope, freeing more blocks. There's no noise, no dust rising like a storm, there's rearrangement. and rearrangement is enough to change the navigatability of a stretch that looked great yesterday. Some ask, and what if it's all rock after all? Aren't there solid places? There are large slabs and blocks, of course, sometimes even with visible fractures, supporting small voids in mini cliffs. But almost always, underneath, there are voids. A rubble-pile isn't a cracked monolith, it's a patchwork quilt with pockets of air, of vacuum in this case, between the pieces. That makes drilling and anchoring risky. You can punch through the debris tabletop, enter a void and jam the tool you didn't want. Or worse, create a fault along which the slope slides. The best strategy is usually touch and go, sample and go, with minimal momentum transfer. Space weather adds its wear. Solar and background radiation, micrometeoroids, and thermal swings decompose minerals, darken surfaces, and change optical properties. That's great science for those who want to read surface age by colors and spectra. It's terrible for navigation by appearance. What's shown yesterday as fine and safe may shine differently tomorrow, just because the skin heated and cooled one more time, producing new microcracks. And if a region darkens from levitated dust deposition, the camera can lose the contrast it used as a reference. The scientific value, on the other hand, is enormous. Rubble-pile slopes are laboratories of granulates in low gravity. They show how materials organize without cement, how avalanches start without a big trigger, how spin reshapes entire surfaces over geologically short times. These processes matter for understanding asteroid formation, orbital evolution, because of Oort, which the shape feeds, regolith dynamics on small moons, and even asteroid deflection techniques. Knowing whether a shove will unmake the pile or move it as a block is the difference between success and strategic error. As for what makes this a frightening place, you can summarize without losing nuance. First, the margin is minimal. Millimeters and centimeters decide between stable and slipped. Second, the feedback is bad. When things start to give, you hardly get a sensible warning. Sound doesn't travel, dust rises slowly, motion is discrete, and when you realize it, your body or your vehicle already has just enough velocity to be past the point of return. Third, rotation tweaks the rule. A safe spot today can become unkind tomorrow because effective gravity dropped a bit at the equator, or because the sun's angle altered a layer's cohesion. Fourth, tools that work on larger worlds become risks. Wheels, harpoons, digging, jets. Here, less is more. How to proceed then in this scenario? Slowly and with redundancy. Measure actual slope, not apparent slope. Check block density per square meter. Cross thermal maps to understand where material works more, with roughness maps to see where the slope drains. Avoid edges with bridges of blocks, and prefer depressions with ponds when the goal is to collect grains, but only if there's a guaranteed way out. Near the equator, remember that effective gravity drops. The temptation to land on flat ground needs to be offset with a takeoff plan that doesn't depend on friction. In inclined areas, same treatment. Touch at minimal speed, absorb the impulse in a spring that doesn't return the bounce, and leaves before the lifted dust comes back as drizzle. If you want a synthesis image, it's this. Rubble-pile slopes are conveyor belts that sometimes pretend to be stopped. What changes from hour to hour is little, but enough that a map made in the morning already deserves doubt in the afternoon. And that's exactly why this environment makes the list. Not for rarity of danger, but for abundance of simple ways to err. It's the granular version of a small mistake that becomes big. Now we can keep the logic of treacherous terrain, but swap granulate in ridiculous gravity for hard ice at extreme temperature and almost no illumination. The permanently shadowed regions in polar craters, the cold traps on the moon and Mercury, where the sun never reaches and everything that falls tends to stay for millions of years. It's another kind of trap. It isn't the slope that moves, it's the cold that doesn't yield. Cold traps are regions at the bottoms of craters near the poles of the Moon and Mercury that never see the Sun directly. Because of these worlds' near-zero tilt, the Sun circles low on the horizon. If the crater rim is high enough, light never enters. The result is simple to state and hard to face. Environments so cold that volatile molecules, water, carbon dioxide, ammonia, and the light organics arrive, lose energy, and get trapped for ages. The scientific appeal is enormous. The operational problem, ditto. There's no blue or red to charm the camera. There's constant darkness, cold of tens of Kelvin, and terrain that mixes dust, ice, and rock in ways our ground intuition doesn't get right at first try. It's close by, it's accessible, and precisely for that reason, it's scary. Everything seems easy until you start listing what in fact has to work all at once. Geometry is the first step to understanding why these cavities become natural freezers. The Moon has minimal obliquity, Mercury even less. At polar latitudes, the Sun is always skimming the crests. A step of a few kilometers at the crater's edge casts shadow forever on the floor. Without direct light, only indirect illumination remains, diffused glow from the sky, wall reflections, and a bit of thermal infrared from the surroundings. That's far too little to warm anything. On ordinary lunar nights, surfaces already plunge in temperature. In permanent shadows, the floor goes to tens of Kelvin, so cold that in some places on the Moon, values lower than on Pluto under weak sunlight have already been measured. On Mercury, the contrast is starker. A few kilometers away, in the lit side, the ground reaches hundreds of degrees. In the dark hole, the thermometer drops to values where water would be brittle glass. The terrain isn't pure ice nor pure rock. It's regolith, that soil of dust and fragments with layers, pockets, and crusts that vary from little crater to little crater. In stretches, very fine grains form a soft carpet with low thermal conductivity. The incoming energy doesn't penetrate, the cold sustains itself, and any weight sinks centimeters as if in flour. Elsewhere, there's cold sintering, grains that, over enormous times, gained rigid contacts by diffusion at very low temperature, forming a little crust that looks firm and is just crust. Where there's enough water, a lunar permafrost forms. Ice and dust bound, hard, giving traction until a heat front from equipment, from a gas leak, from the simple presence of a warm body, unglues the cement and undoes the firmness. It's terrain that changes mood with the few watts. How did those molecules end up there? By two main paths. One is impacts. Comets and asteroids bring water and organics, hit, vaporize, and the products fly, hop, and partly land in regions cold enough not to leave again. The other is the world's own breathing without air. Solar wind, atoms hit minerals, reactions release hydrogen and oxygen, micro-impacts recook everything and create a traffic of ballistic hops in the exosphere. Where it's warm, each hop returns the molecule to space. Where it's very cold, the hop ends. That's why Mercury's ice maps show radar-bright deposits near the pole, some covered by a layer of darker material that acts as a thermal blanket, and why the Moon's polar regions return hydrogen signals and signatures of mixed ice in the regolith. No deposit is uniform, all are selective. The neighborhood of a wall with enough reflected light can stabilize a slightly higher island of temperature and change everything within tens of meters. Heat physics rules the rest. In an ordinary place, you turn on a heater and the heat leaves by convection to the air, by conduction to the ground, and by radiation to space. Here, there's no air, only radiation and conduction remain. Conduction in regolith is poor. Radiation in a pit surrounded by cold walls sees little hot area to exchange with. That creates a counterintuitive situation. Keeping equipment lukewarm requires constant energy and, at the same time, Any leaked heat contaminates the science and ruins samples. Measuring ancient ice with sensors that warm the surroundings is the same as melting the evidence you wanted to see. That's why self-contamination is an ugly, frequent word in these studies. The vehicle itself outgasses residual water, solvents, and plasticizers, and all that condenses back on cold surfaces, exactly where the lenses, filters, and collectors are. In a vacuum chamber, we already suffer with this. In the polar pit, we suffer in real time. Power is a drama of its own. Without direct sun, solar panels don't work. Batteries deliver less in extreme cold. Radioisotope generators solve it, but aren't always an option, and still bring the curse of the previous paragraph. They heat the surroundings. Even if the plan is touch and go, descend a sample and leave, someone must keep lines, seals, and actuators warm during the darkest hours. There are clever solutions, like leaving the power plants on the crater's ring, where there are places with almost permanent sun, and sending messenger robots into the interior, connected by power and data cables. But cables tension, freeze, snag on rocks. Line-of-sight repeaters require a mast, which must not freeze. Everything seems simple until you draw the thermal and mechanical scheme. The same proximity that would sell the project, it's the moon, not Mars, exacts a price and low-temperature details. Navigation and perception stop being extras and become protagonists. In total shadow, RGB cameras become lost tourists. You swap color for intensifiers, active infrared, LiDAR. Those sensors in turn suffer from low contrast, tricky reflections on ice crystals, and fine dust hazes raised by the arrival itself. LiDAR solves geometry but needs clean windows. The windows get dirty, the loop closes. To top it off, the horizon disappears. The field of view is a black cauldron with cutouts. The solution is to bring artificial references, beacons with light on the crater rim, reflective markers, and accept that landing and locomotion are centimeter choreographies. It's operating by instruments, not by eye. Communication also gets complicated by pure geometry. Inside a pit, the REM cuts line of sight to Earth. You either use a repeater on the ring, a rover bridge, a mast, or a small stationary platform, or accept periods of silence. On the moon, you can bankroll an almost continuous solar repeater near the poles. On Mercury, the thermal management of that repeater becomes another project. The same sun that never enters the pit scorches the REM with the long day and blistering illumination. You alternate between extremes literally. On the REM, the engineering is desert. At the bottom, cryogenics. Dust, the moon's old acquaintance, gains extra behavior at these latitudes. The electric field that forms at the terminator, the line between light and shadow, can lift small grains. Inside craters, that electrification is different, less photo emission, but the REMs are zones of different potentials. In repeated hops, grains can migrate, sticking where they shouldn't. The same electrons that help keep ice for millions of years give, day to day, the kind of nuisance that fills integration notebooks, a layer that appears on a panel, a lens that at the right temperature becomes the perfect target for condensation. Materials and mechanics work on a razor's edge. Ordinarily oils and greases freeze, elastomers stiffen, some metals change behavior under very large thermal cycles. With no atmosphere to cushion, every touch is dry. The super cold, hard ground turns vibrations into little shocks that propagate without much dissipation. The solution is less glamour and more discipline. Dry bearings or solid lubricants, thermal protections that don't leak heat to the target, shutters and doors to seal optics when they aren't measuring, and above all, an operating profile that accepts moving slowly. Instead of sweeping area, you pick points and take care not to ruin what you came to get. Mercury adds its set of paradoxes. It's the closest planet to the Sun. It has polar ice. The how arises from the same ridiculous obliquity as the Moon and the harshness of vacuum. In many deposits, the best explanations call for a dark lid over the ice, organics and dust that heat in sunlight and insulate the white layer below, a counterintuitive blanket. In smaller or more recent craters, there are signs of more exposed ice without a lid. In all cases, what radar calls bright isn't photographic brightness. It's an electrical response consistent with voluminous ice. Operating there would have required dealing with a hyper-hot rim with a months-long day and a hyper-cold interior that you must not sterilize with your own presence. It's a natural laboratory of absurd gradients. Why then is it worth the effort? Because these pits store archive. If ice samples return layers separated by dust, they tell a delivery history. Comet outburst, epics of volcanism, changes in the solar wind, even marks of the sun's extreme events. On the Moon, beyond pure science, there's the practical side. Water as a resource, propellant, air, shielding for polar operations. Approaching with scientific respect ensures that future use doesn't destroy the record. The cold trap has worked for millions of years. A minute of poorly planned hot exhaust becomes a decades-long regrets. The frightening label, IMEN, comes less from dramatic risk and more from the sum of constraints. Almost everything that helps in normal places hinders here. Light contaminates. Heat melts the evidence. Panel sees no sun. Battery performs poorly. Thruster lifts dust and evaporates ice. Wheel skids on a fluffy powder or cracks a crust you wanted intact. Open optics became a frost target. And since the sensory signals are weak, error is expensive and shows up late when the reading is already biased by your very presence. Loki Patera is, roughly speaking, a lava lake on the scale of a city-state, something like 200 kilometers in diameter, with irregular horseshoe-shaped rims and a thermal glow that rises and falls in cycles. On Io, the most volcanically active moon in the solar system, none of this is an exception, but Loki has a behavior that sets it apart from the rest. It doesn't just explode and that's it. It turns inside out. A solid crust forms on the surface of the lake, cools, thickens, loses buoyancy, and, from time to time, sinks in large panels, revealing fresh lava underneath. This process runs like a wave of renewal that crosses the basin over weeks, rekindling the thermal glow as the old shell sinks and the new face comes to the surface. The landscape looks stable from afar, fixed outline, high rims, flatness in the interior, but inside it's a conveyor belt of molten rock. Starting with this mechanism helps to understand why Loki is scary in the right way. It combines extreme heat with predictably unstable terrain. The lava there is probably basaltic, perhaps ultramafic, with temperatures that can exceed 1200 to 1400 degrees Celsius when exposed. In minutes, the newly opened surface creates a dark film a few centimeters thick. In days, the film becomes a plate meters thick. In weeks, the density increases enough for the plate to stop floating. When a section sinks, edges break, trapped gases escape, and the incandescent sheet reappears. None of this needs thunderous explosions. In vacuum, there is no sound. For those who imagine operating there, what bears the name lake behaves like a moving floor factory. What is ground today becomes an open oven mouth tomorrow. Io, as an environment, gives context to this lava laboratory. The moon spins immersed in Jupiter's magnetosphere, with a thin sulfur dioxide atmosphere and pressure variations that depend on day and night. The energy that feeds the volcanoes comes from tides. Io is rhythmically kneaded by the gravity of Jupiter and the other moons, and this kneading generates heat inside, keeping rock molten and a recharge cycle for chambers. This heating is so efficient that Io's mantle, on the scale that interests us, behaves like a reservoir always at the ready. The result is dozens of active paterae, plumes that rise hundreds of kilometers, and colorful deposits of sulfur and frozen SO2 painting the ground. In this chorus, Loki is the deep-voiced soloist, more regular, broader, more industrial. Loki's very historical regularity, brightness cycles that were once about 500 days, then varied, then changed again, is another clue that we are dealing with a system that self-organizes. If the crust forms at a certain rate and sinks when it reaches a certain thickness, you get a natural metronome. Every so often, an overturned front fires in one sector and traverses the basin, renewing the surface in bands. For those observing in the infrared, this translates into a hot map that sweeps the lake. For those imagining engineering on the rim, this translates into short deadlines for any operation that depends on reliable footing. The rim looks inviting, a rocky overlook with some traction, away from exposed lava. But the interior is not a quiet pit, it's a carpet that pulls downward. Add gases to this picture. Io exhales sulfur dioxide in quantity. The local atmosphere over Loki is denser during the day, thinner at night, and plumes from other regions can sweep the neighborhood. At very high temperatures, sulfides and SO2 come off, expand, and freeze onto nearby cold surfaces, including on instrumentation. What looks beautiful in photos, bright fields of sulfur dioxide frost, becomes a technical enemy. Deposits that cloud lenses, seal gaps, dull radiators. And as Loki alternates phases of high and low glow, gas convection over the basin changes regime. On days of exposed lava, the hot flow cleans. When the crust dominates, cooling favors condensates on the rims. With each cycle, sensors and structures would be tested by grime and temperature. The surrounding terrain does little to help. Io's Patera are depressions with steep walls and broken pavements. Pieces of dark crust, glued and cracked, make a mosaic where friction is better than on lunar ice, but the internal cohesion of the material is deceptive. Repeated heating and cooling creates fractures. Tidal stresses shift phase over the course of a Jovian day. Microtremors, earthquakes of thermal and tidal origin, readjust blocks. On a rim that holds in the morning, loose slabs may appear in the afternoon, especially when the overturned front passes beneath and redistributes buoyancy. It's easy to imagine a stretch near the rim that seems safe, turning into a ramp. The old shell detaches and slides, opening a mouth of lava where there used to be a ceiling. The step that was advancing 1 meter becomes backing up 10. Another more discrete risk is thermal, in the opposite sense. In cold environments, the problem is keeping everything warm. On Io near Loki, the problem becomes not frying. Cables, seals, oils, and resins commonly used don't tolerate 200 to 300 degrees Celsius, let alone 4 digits. The obvious solution, staying farther away, competes with the reality that sulfur gases and dust travel. The alternative solution, shielding and cooling, competes with mass consumption and, ironically, with the chance you'll become a cold island where sulfur dioxide and sulfur decide to condense. With every attempt at protection, the risk of self-contamination arises. You become a pole of ice and dust. The dust steals emissivity. Emissivity worsens cooling, and the cycle becomes a trap. Jupiter's radiation is another member of the opposing team. Io orbits immersed in intense belts. Electronics without hardening suffer from dose and from single events. Bit flips, lockups. Loki doesn't worsen this by itself, but adding lava plus sulfur plus radiation doesn't help. Extra windows, doors, cables, and power headroom, everything that compensates for heat and grime, must itself survive the particle bath. In other words, the design margin vanishes quickly. Little room for error remains when you need to be resistant to 3 hostile environments at the same time. The rarefied atmosphere brings a curious effect to local pollution. In near total vacuum, gas jets exit and expand ballistically. If there is any local gas, it's still too thin to cushion particles or dissipate heat by convection. This means lava spatters, microfragments, and solidified droplets travel freely before falling. Even a few kilometers from the rim, surfaces accumulate a patina of glasses and sulfides over days, enough to change optical and thermal properties. It's drizzle from a volcano, only without wind. The direction is statistical. governed by the position of the active sources in that overturned cycle. From a geophysical point of view, Loki is a rare gift, a window into large-scale lava lake dynamics. On Earth, the lava lakes at Kilauea and Nyiragongo offer similar lessons, forming crust, convective belts, plates that break, but none with Loki's size and regularity. The idea of floating plates that sink due to loss of buoyancy explains the waves of brightness. The hypothesis of feeding through conduits connected to a reservoir explains recurrence. The interaction with tidal stress explains why the clocks change from time to time. Each cycle seen in the infrared, each thermal mapping that traces the advance of the overturned front is another line in a manual of magma rheology that we cannot write in the lab. That manual, however, is written in a rather unfriendly typeface. Io's true color is a mosaic of yellows, oranges, and blacks. The contrast can mislead sensors when the sun is low. The absence of an atmosphere makes shadows very dark, and reflection on glassy surfaces near the lake rim creates ghosts for vision algorithms. Navigating by image needs specific training. Saturated glow in the infrared misleads photometers. The repetitive texture of cracked plates confuses point matching. The practical recipe is the same as we learned on comets and in cold traps: inverted for heat, LiDAR for geometry, calibrated thermal for activity, shutters for optics, opened only when taking measurements, redundancy in attitude sensors, and respectful distance from the rim. Chemistry also makes the "why it's complicated" list. Sulfur and sulfur compounds attack metals in ways that don't show up in dry terrestrial environments. Solid sulfur deposits can weld caps and rings. SO2 that sublimates and refreezes in short thermal cycles creates temporary seals where you most hate sealing. Sample intakes, filters, heat outlets. Designing for Io requires choices of materials and geometries that don't create little corners where condensates accumulate and jam. In other words, less is more. Continuous surfaces, rounded corners, and no narrow path that depends on staying clean by luck. There is, of course, a practical side that seduces any team. Loki is so bright in the infrared that you can see it working from very far away. This enables coordinated campaigns that measure the speeds of overturned fronts, the extent of freshly exposed areas, and the cooling times of plates. In different seasons, speeds change, directions swap, the overall cadence lengthens or shortens. Signs that the reservoir supply and the schedule of tidal stresses are not constant. Science is grateful. You can test models, tweak parameters, compare with terrestrial lakes, extrapolate to hot rocky worlds like 55 Cancri E, where lava may be more than a metaphor. The problem is that the closer we want to look, the longer the list of things that can go wrong grows in parallel. On balance, Loki Patera is frightening because it combines 5 truths that rarely go together: heat that gives no respite, flooring that becomes ceiling and becomes flooring again, gases that dirty and glue, radiation that drives electronics crazy, and time that runs against time-consuming procedures. There are no hidden monsters. There is active physical process on a large scale operating before your eyes. The margin for improvisation is small. If on Titan the enemy was silent accumulation, and on Venus constant pressure, at Loki the adversary is inevitable renewal, the certainty that what is solid today will sink, and that your plan must be good enough to work before that happens. On Mars, the danger doesn't come from lava, nor from crushing pressure. It comes from something seemingly light, fine dust blown by thin air. It seems harmless until, from one day to the next, the planet raises so much material that the sky turns dark brown, the sun becomes a dull disk, and the landscape vanishes. These are the global dust storms, the events scientists call planet-encircling dust events. They aren't frequent, but when they happen, they dominate everything: power, navigation, communication, temperature, planning. They frighten because they swap the entire mode of operation for weeks or months, and there's no way to switch off the planet to wait it out. The basis of the phenomenon is simple. Mars has a low-density atmosphere, about 1% of Earth's, but large enough to transport dust that is almost talcum. Normal wind doesn't have the force to knock over big things, and that's the catch. It doesn't need to. It only needs to set the right grains in motion. First, sand grains make low hops, saltation, hit the ground and lift much smaller particles that, by themselves, wouldn't budge. Once the fine cloud is in the air, it changes the energy balance. It absorbs solar radiation, heats layers of the atmosphere, messes up temperature gradients, and with that, feeds more wind. The wind then carries more dust, which heats the air more, and the positive feedback lever is armed. A local storm becomes regional. If it reaches a critical size, the process feeds back to the point of involving much of the globe. The practical result is that the light disappears. Those who depend on solar panels see production drop dramatically, and it's not just the immediate shadow, it's the combination of dark sky with dust deposited on the panels. On normal days, small dust devils sometimes clean panels by chance, but in a global storm, the opportunities for cleaning almost always lose to continuous deposition. The classic case is of solar platforms that enter deep power-saving modes, and if the batteries can't endure long stretches with just a few watt-hours per day, don't come back. Those who use nuclear generators breathe a bit easier, but are not immune. Cameras start operating at max ISO. LiDAR and lasers need more attempts to get useful returns. Spectrometers see signals washed by scattering, and a simple image mosaic takes much longer because the signal-to-noise ratio plummets. Navigation suffers for a prosaic reason: lack of contrast. In clean Mars, the sky has that buttery hue, the horizon is legible, rocks cast decent shadows. In thick dust, everything becomes brown Play-Doh, edges disappear, the terrain looks flatter than it is, and the sense of distance worsens. Rovers rely on stereo vision and algorithms that measure texture to compute relief. When the texture becomes homogeneous noise, the software gets cautious, and rightly so. Sometimes the vehicle simply doesn't advance because uncertainty has grown. For operators, patience is part of the plan. The pace drops by choice, not by defect. Martian meteorology adds as a bonus a curious thermal effect. Without dust, deserts cool a lot at night. With dust, the atmosphere holds heat like a thin blanket. The day becomes colder at the surface because light is blocked, and the night becomes less cold because the dust re-radiates in the infrared. That seems like a detail, but it creates new ground behavior. Certain stretches lose the stiffness they had at dawn. Small thermal crusts vanish. Sand that previously held a wheel begins to give way. The opposite also happens. Regions that would normally become tricky at dusk start to respond differently. None of this topples a vehicle by itself, but together it pushes all the drivability maps a few meters this way and that. If the question is, what is the real danger? The answer has two layers. The first is power. Without direct sun, solar missions go on a severe diet, with schedules reduced to a few commands per day, or none. Cameras and heaters compete for the same watts. Motors wait. If the episode lasts long, the batteries dive into deep cycles that shorten their useful life. Even for those with RTGs, electronics and operations enter low light mode, shorter images, less science per hour, more time spent on checks. The second is information. Dust in the air and on lenses steals detail. Sensors get nearsighted. Terrain interpretation becomes conservative and needs to be. There's also the electrical part of the story. Dry dust colliding and rubbing charges up. In the lab, in situ measurements, it's already been seen that Martian grains can acquire tribal electric charge, and that modest electric fields form in dust devils. In a global storm, the number of interactions skyrockets. We're not talking Hollywood lightning, but a more nervous environment, with potential for discrete discharges or for interfering with sensitive readings. For hardened electronics, this is an annoyance, not sudden death, but added to everything else, the cold of night, the smothered daytime heat, vibration, dust, it becomes yet another constant pressure on components already operating at the limit. Abrasion is another silent enemy. Fine grains strike slowly, but they strike millions of times. Lenses lose transparency, mirrors become purplish, painted surfaces change albedo, exposed connectors gather a thin layer of particles that seems harmless until it becomes a thermal insulator or jams a ring. And instruments that depend on open apertures, spectrometer inlets, laser windows, filters, shutters become routine. Open only when in use, close right after, a discipline that consumes time and mechanical cycles. And each cycle, of course, also ages the part. Curiously, winds are not as big a mechanical hazard as an Earth-trained brain imagines. The light atmosphere doesn't push with the same force as a terrestrial gale. Panels and masts don't go flying just because the anemometer spiked. The damage is less punch and more sandpaper. Layer by layer, surfaces change. On the other hand, local flows accelerated by slopes and craters can raise dust jets that act like spray directly in an instrument's face. And, as always on Mars, topography rules. The same global storm can be a mild nuisance in a valley and a total blackout on a high plateau, simply because local circulation channels dust one way and not another. The orbital side of the story adds another class of problems. Satellites around Mars that depend on optics and radar see data quality drop when dust is high. Trajectory corrections and image planning come to depend on opacity forecasts, the famous TOE, which change from one day to the next. Communication with Earth in general holds. The radio signal passes through dust, but data rate may drop by operational decision. There's no point in filling the queue with images if they'll all come out dark. The scientific rhythm changes by choice, and that's more frustrating than dangerous. But for operations that depend on constant map updates, frustration becomes a real limit. One contradiction that helps explain why this is on the list: the same planet that sometimes cleans panels with a capricious breeze is the planet that, in a global episode, pulls the plug for weeks. The same air that doesn't have the strength to push a rover downhill has enough energy to suspend dust and dim the sun. The same desert that gives a clear horizon turns into a uniform wall of brown. It's not the wind that knocks you down, it's the persistence of the process, the duration, the scale, the ubiquity. When the dust decides to stay, every operational decision becomes more expensive. There's also the post-storm memory. When the sky clears, the planet doesn't snap back to normal. New deposits redistribute what was light and what was dark, change how much heat the ground absorbs, shift the times of maximum and minimum temperature, and that writes another round of adjustments for traction, for risks of getting stuck, for the quality of thermal readings. Panels may even get some late cleaning, but if the storm was severe, they usually end up less efficient than before. And the dust that got where it shouldn't takes time to be removed, if it can be. Shutters start to scrape more, filters clog more easily, and the time budget devoted to health and maintenance fattens. If we want a useful mental image, we can think of three scenes. In the first, the sun is an opaque circle without shine, barely casting a shadow. In the second, the camera tries to focus and everything is grainy. The software asks for another shot and another, until someone decides it's enough not to miss the path. In the third, the team turns on thermal and the graph shows nights less cold than yesterday and days less hot, and the curve of available energy per sol falls like a stone. None of these scenes is dramatic by itself. Together they define an environment that dispenses with spectacle to be hostile. Why is it so worth studying? Because global storms are windows into the climate physics of an entire world. They show how radiative feedbacks accelerate circulations, how small relief decides big meteorology, how dust participates in chemistry, including processes that produce and move strong oxidants like perchlorates. For engineering, they teach how to design missions that don't fall apart when the light fades. And thinking of a human future, they define the basics: how many days a habitat needs to endure without full solar generation, which filters work when everything wants to become a filter, how to keep antennas clean without someone outside with a broom. Moving on, we can leave Mars's brown for a larger scale absolute black, the Oort Cloud, where the solar system dissolves into dark ice, distant, almost without sun, and where the threat ceases to be weather and becomes trajectory, objects that sleep for millions of years and sometimes decide to fall. It's the opposite of a storm that lasts weeks. It's a silence that lasts ages, broken by visits no one invited. The Oort Cloud isn't a place with scenery and a horizon. It's a vast, almost spherical volume that envelops the solar system far beyond Neptune. It's the outskirts where the sun no longer rules with full authority and starts having to share custody of each icy body with the galactic gravitational field and the occasional passing star. That's precisely why it makes our list. It's the source of the most unpredictable visitors we can get. Long-period comets that arrive from any direction, very fast, and sometimes large enough to turn a statistical fluke into a global problem. For bearings, think of the solar system as a neighborhood with zones. Out to 30 AU, astronomical units, you have the planets. A few tens of AU beyond that lie the more domestic trans-Neptunian objects in the Kuiper belt. The Oort Cloud begins thousands of times farther out, thousands to tens of thousands of AU, possibly extending to 100,000 AU, i.e. a non-trivial fraction of a light year. Out there, sunlight weakens so much that the equilibrium temperature of icy grains and blocks bottoms out near the floor of the universe, just a few Kelvin above the cosmic microwave background. In simple numbers, at 10,000 AU, a dark object stabilizes around 3 to 10 K. Extreme cold isn't a figure of speech, it's the baseline. The outskirts aren't perfectly empty. It's a depot of trillions of small, icy, dusty bodies, from pebbles to mountains, leftovers from the era of planet formation. Many were flung outward in the solar system's youth, scattered to the fringes by the giants, Jupiter, Saturn, Uranus, Neptune, and tamed by the galactic tide until they settled into a reservoir only loosely bound to the sun. You can picture an outer, more spherical layer called outer Oort, and an inner, denser, more compact one, sometimes called the Hills Cloud. However you slice it, the key word is the same: weak binding. The sun still wins, but barely. So what knocks an object off that icy shelf and sends us our way? 3 agents: the galactic tide, that slow background tug exerted by the Milky Way on the whole ensemble; encounters with stars that pass relatively nearby every few million years; and now and then, a shove from a denser interstellar gas cloud crossing the neighborhood. Any of these perturbations can tweak an Oort Cloud body's orbital energy and orientation. Most nudges just swap one shelf for another, but a fraction get just the right conditions to fall inward. The eccentricity shoots up, perihelion drops, and something that slept for ages becomes a long-period comet headed for warmth. Here's where the frightening gets concrete. Unlike near-Earth asteroids, NEOs, which orbit near the planet plane, long-period comets arrive at any inclination, literally from anywhere in the sky, and they come fast. By the time they cross Earth's orbit, they're already moving at tens of kilometers per second. They also change behavior as soon as they warm up. They start to sublimate, launch asymmetric jets, add non-gravitational drag, and often fragment. Translation: even after you measure the trajectory precisely, you have to budget for effects that didn't exist a few months ago. Models help, but they don't tie everything down, and the clock is ticking. Warning time is the variable that weighs most in the risk equation. For a typical NEO, we sometimes have years or decades of lead time. For a first-time Oort newcomer, good detections may happen only once it has entered the inner solar system and started to brighten. Depending on size and albedo, that can mean months of margin, sometimes less. And because the object changes personality, activity, fragmentation as it approaches the sun, uncertainty about the real risk grows just as the maneuvering window shrinks. It's not that there's never time, it's that the time you get is the hardest to use well.
If you're thinking planetary defense, the strategy gap jumps out. A known asteroid can be nudged with early deflection missions. Millimeter-per-second touches, applied many years in advance, translate to thousands of kilometers on encounter day. Long-period comets demand a different game. Very early detection, hard. Rapid activity assessment, hard. And an action that works with a narrower window, hard. In some scenarios, talk of intercepting and fragmenting makes things worse, turning one big single target into a swarm of smaller projectiles with the same total energy. The ideal is to deflect, and deflect early. The Oort regime rarely grants that luxury. Why not map the Oort Cloud once and for all? Because by definition, it's nearly invisible. The objects are small, dark, and cold. They emit no light of their own and reflect very little sunlight. Seeing them directly, as stationary pinpricks, is beyond current telescopes except for very rare cases of large objects already on the way. Indirect techniques help. Statistics of observed comets, occasional stellar occultations, when a dark object crosses a star and dims it for milliseconds, dynamical models refined by star catalogs that predict future encounters. It's painstaking, building a probabilistic map of something that refuses to be photographed in aggregate. And what if we go there? Also hard. Around 100 AU, where the heliosphere ends and the solar wind loses its arm wrestling match with the interstellar medium, sunlight is barely useful for power or navigation. At 10,000 AU, any mission with present-day tech would outlast a human career, and one-way communications delay would be on the order of 2 light months. At nearly 100,000 AU, the delay exceeds a year. You trade the scientific thrill of touching a source object for a multi-generational project that needs robust nuclear power and electronics that can withstand the interstellar radiation environment for decades. Great as a precursor interstellar mission, as an Oort catalog, the math doesn't close. None of that diminishes the science, quite the opposite. The Oort Cloud is an archive of how the solar system was born and reorganized. The mix of ices, water, CO, CO2, ammonia, methanol, organics, preserves the chemistry of our cradle, perhaps with a signature of where the sun formed in the galaxy, in a crowded cluster with strong ultraviolet light, in a quieter zone. The statistics of comet orbits tell how far the giants migrated in the first few 100 million years. Each long-period comet observed with spectrometers is a free sample from that archive. Its tail reveals composition stored thousands of AU from the sun, far from any solar cooking. The galaxy itself writes lines in the script. Every few million years, a neighboring star passes close enough, galactically speaking, to stir the Oort Cloud. Close here means tens of thousands of AU, far for us, short for the cloud. Most passages merely tweak the comet flux around the edges. Occasionally, a lucky or unlucky alignment triggers a comet shower, a statistical excess of new visitors spread over millennia. No Hollywood here, no lights going out, just a raised chance we'll see more comets in the next few million years than in the last few. For a species that plans in centuries, that galactic time is both immense and relevant. Operationally, the Oort Cloud is unnerving for a specific vulnerability. You don't control the clock. It's an environment where risk comes as occasional beams of trajectories that thread your neighborhood, and you only know they exist when heating physics starts to light up the comet. Even when there's time to observe well, the jets themselves mess with fine navigation. The rotating nucleus acts like a watering can, imparting tiny thrusts here and there. Each rotation changes the direction. The predicted orbit demands corrections. For astronomy, that's a fun challenge. But for planetary defense, it's math that demands fast communication, global coordination, and decisions with little room for let's wait for more data. There's a second frightening place layer worth noting, the boundary with interstellar space. The outer Oort Cloud surely rests beyond the heliopause, where the solar wind yields to the galactic wind and the interstellar magnetic field lines take control of the plasma. Out there, cosmic ray fluxes are higher, energetic particles penetrate more deeply, and the sun's weather doesn't help. An object that lived outside forever has been bombarded by that environment for billions of years. When it falls inward, it brings a skin processed in ways labs love to decode and instruments must respect: darkening, roughness, cohesion. If you want the concrete risk scenario that puts the Oort Cloud on this list, the summary is straightforward: low probability, very high impact, with a short window and a target whose behavior changes. A single nucleus tens of kilometers across, arriving with the wrong geometry at the wrong time, is the kind of risk you can't solve with improvisation. The good news is we can improve our side of the equation a lot. Wide-field telescopes scanning the sky continuously to find the newcomers, precise star catalogs to forecast perturbations, simulations that include cometary activity to refine trajectories, and a response culture that accepts that, with long-period comets, deciding early matters more than deciding perfectly. Curiously, this place we can't see changes how we look at places we know well. Every new comet that cuts the sky is a message from the Oort Cloud, and each message forces us to practice what matters: discover, characterize, predict, decide. That's why the dark outskirts teach operational humility and at the same time deliver pure science, primordial chemistry, galactic dynamics on the solar neighborhood scale, the memory of planetary migrations. Narratively, it closes a neat arc. After environments that attack us up close, radiation at Jupiter, dust on Mars, lava on Io, here's one that attacks from afar, with ammunition that chooses its hour.
Near the planets, the sun rules. It blows a steady wind of charged particles, drags along a magnetic field stretched like rubber bands, and inflates a bubble around everything, the heliosphere. But far away, well past Neptune, that wind slows, heats, turns turbulent, and finally gives way to the interstellar medium. The boundary where this happens has surnames. First comes the termination shock, where the sun's supersonic wind becomes subsonic, then the heliosheath, the thick, messy region, and finally the heliopause, the skin of the bubble, the point where our wind no longer beats the galaxy's wind. It isn't a visible wall, and perhaps that's why it's unsettling. An invisible limit where energetic particles, magnetic fields, and turbulence trade the rulebook of one entire system for another. The scenery doesn't change color, but the physics changes owners. The best way to see why this place belongs on our list is to play the film in order. Start with the solar wind, flowing at hundreds of kilometers per second. As long as it's faster than the speed at which disturbances propagate in the plasma, the medium's sonic alphonic equivalent, it doesn't really feel what's coming the other way. But as it expands, that wind loses energy by two routes. It spreads into an ever bigger bubble, and it undergoes charge exchange with neutral atoms drifting in from interstellar space. Those neutrals dip in, steal electrons from solar wind ions, become newborn ions, pickup ions, and get carried along. It sounds like a detail, but these passengers increasingly ride the brake. Eventually, the flow can't sustain its speed, and a break forms, the termination shock. Upstream, cooler, fast, organized wind. Downstream, hot, slow, turbulent wind. This heating isn't beach weather. At the shock, some flow energy becomes heat and particle acceleration. The pickup ions, born slow, then swallowed by the flow, become favored customers of the accelerator. They gain extra energy and make up a population of anomalous particles, a notch below classical cosmic rays, but still far more energetic than the ordinary wind. The region just past the shock, the heliosheath, is a soup of crumpled magnetic fields, turbulence, jets, and vortices. It's the opposite of a calm vacuum. Structure everywhere, only invisible to the eye. Farther out lies the heliopause, the bubble's skin. On one side, the sun's carried magnetic field, on the other, the interstellar magnetic field, the galaxy's IMF, not to be confused with the monetary fund. These fields aren't neatly aligned, they drape over one another, and in many places reconnect. Field lines break and rejoin, releasing bursts of energy and opening windows through which particles cross. It's a soft boundary pocked with holes that shift around. Operationally, that means two things. First, energetic particle doses can vary a lot in a short time. Second, you can't treat the heliopause as a smooth contour. It wrinkles, quivers, and breathes with the solar cycle and with the conditions of interstellar space. What's scary about just passing through? Start with the radiation bath. Inside the bubble, the solar wind and magnetic field filter some galactic cosmic rays, very high-energy particles from every direction. Near the skin, that filter weakens. Outside, the cosmic ray flux jumps. Inside, it oscillates with the solar cycle. In hardware terms, that's higher total ionizing dose, more single-event effects, random bit flips, lockups, and accelerated aging of sensors, detectors, and electronics. You leave the sun's weather and enter the galaxy's weather. Second, noise. Literally, plasma in the heliosheath is a sea of waves and turbulence. Instruments that measure fields and particles, essential to knowing where you are relative to the shock in the skin, start recording highly variable signals. It's not that they can't be interpreted, they can, but it's like driving in fog with raindrops all over the windshield. You need to average, cross-calibrate, and accept that no single sensor tells the whole story. This imposes discipline. Sample slowly, calibrate often, and tolerate long integrations to separate the pattern from the splatter. Third is both geometric and temporal. None of this is fixed. The distances to the termination shock and the heliopause vary with the 11-year solar cycle. When the sun is more active, it blows harder. The bubble inflates. In quiet years, it deflates. And the outside wind and field aren't homogeneous. The heliosphere meets clumps, direction changes, pressure differences. Practical result, the place you cross the heliopause in one decade may not be the same in the next, and the heliosheath, the turbulent transition region, thickens or thins over time. Any plan that depends on arrive there at XAU must become arrive when the instruments say you have. There's also a power and energy gotcha that pretty diagrams hide. Any mission reaching this frontier is already at ultra-long range, hundreds of times the Earth-Sun distance. Solar panels are useless. That leaves nuclear power, RTGs, which in turn decay year by year. In other words, just when the physics gets most interesting and your sensors need more time and energy to integrate, the spacecraft's power plant delivers less. Add a weak comms link, antennas see microscopic signals. Every bit takes time, and any retransmit costs precious watts and hours. The environment asks for patience, logistics supply parsimony. That tension between I want to measure more and I can measure less is part of the fear factor, not exploding hostility, but limiting hostility. Another oft surprising piece is the role of energetic neutral atoms, ENAs. When a hot ion in the heliosheath steals an electron from an incoming neutral atom, it becomes an energetic neutral and shoots off in a straight line, oblivious to magnetic fields. They carry an indirect map of the turbulence. ENA telescopes in inner orbit, think satellites looking outward, make images of the edge, even revealing ribbon-like features, preferred structures nobody expected. Translation for our theme: the boundary isn't a spherical shell, it's a patchwork with seams. That amplifies the technical dread. If you need predictability, the place offers organized intermittency, large-scale repeatable signals with small-scale details that change on short timescales. On the risk roster include magnetic reconnection. In plasma, when oppositely directed field lines meet, they sometimes change partners abruptly, releasing energy and spitting out jets and magnetic islands. On small scales, that pops the heliosheath like kernels in a pan. We're not talking hammers smashing spacecraft, but an environment that pushes and pulls particles in fields, jumbling what you measure from second to second. For magnetometers, particle detectors, and radios, it's a surprise generator. Levels rise, fall, pulse, and any algorithm that wants to decide crossed, not crossed, must learn to live with ambiguity. By now someone asks, can you see the change? Operationally, yes, but not with an RGB camera. Crossing the heliopause shows up in counters. Solar wind particles plummet. Galactic cosmic rays surge. The magnetic field's texture changes, not necessarily a single flip of direction, which was debated. And plasma waves take on a different accent. It's like driving off asphalt onto cobblestones without looking down. You didn't see the pavement end, but your steering wheel and your back know. Compared with other environments in this series, the heliopause is a conceptual cousin of Jupiter's belts and quasar jets. The danger lives in particles and fields, not rock, gravity, or heat. But here the risk comes from a regime change. Inside the bubble, engineering learns to play to the sun's moods. Outside, the mood belongs to the galaxy. It's a boundary that changes who writes the rules, and thus changes how you must interpret every reading. It's also the gateway to the local interstellar medium, the neighborhood we traverse as the galaxy turns. The density and composition of that medium vary on timescales of tens to hundreds of thousands of years. In phases when the heliosphere meets denser regions, the bubble can shrink. In rare phases, it could intrude farther into the outer orbits. That matters downstream for cosmic ray fluxes inside the solar system, and speculatively for ionization rates that affect atmospheric chemistry and even cloud formation on planets. Ideas still under study, but reinforcing the message, the boundary breathes to the galaxy's rhythm. Practically speaking, why is this place frightening? Because it concentrates 4 limits at once. A measurement limit, weak signals, high noise. A modeling limit, large-scale reconnection and turbulence that's hard to forecast in detail. An energy limit, little power for lots of curiosity. And a time limit, slow communications, hardware lifetimes waning just when you most need them. There's no avalanche, no giant tide, just a set of subtle constraints that, added up, make you accept an unglamorous truth. The winning strategy is resiliency and thrift. Measure less for longer, bet on redundancy, and let statistics tell you what snapshots won't. Cerberus Fossae, in the middle of the smooth plains of Elysium, is the kind of place that undercuts our intuition about Mars. From afar, it looks like just another stretch of radish desert, flat, uneventful. But when you get close enough to see the lines slicing the ground, long, straight fractures with crisp rims and near-parallel walls, you realize this patch of the planet is still moving. And on Mars, that's an uncomfortable novelty. For decades, the dead world picture fit well. Giant volcanoes, yes, but extinct. Colossal channels, yes, but ancient. Cerberus Fossae makes the list precisely because it breaks that comfortable narrative. It's a set of geologically young tectonic fissures, tied to quakes that keep happening, likely fed by deep magnetism. In an engineer's terms, the ground here isn't a photograph, it's video. At human scale, the scene would go like this. You walk across a monotonous surface, fine sand mantling slabs of rock, and suddenly the landscape opens into a clean score on the horizon, a cut tens of meters wide that runs for kilometer after kilometer, with a discipline no wind erosion can explain. The edges are high and friable, sometimes with internal steps that portray recent collapse. In places, 2 or 3 fissures run in parallel, like the mark of a giant plow. These straight streets weren't carved by water or wind. They tore open when the subsurface was forced upward by magma conduits, dikes, intruding between rock layers. It's the same principle that makes rifts and basaltic islands on Earth, think Iceland, only under lower gravity, thin air, and a stock of ice mixed into the soil. That combination yields its own effects. Where a dike rises but never reaches the surface, the roof cracks and sags. Where it rises into ice, the heat makes vapor, pressure builds, and sometimes discrete explosions spread dark ash around the fissure. This youthfulness isn't marketing. The Fossae themselves cut through smooth deposits of lava and dust that elsewhere sit untouched for millions of years. You see swaths of fresh lava, flow textured surfaces with almost no craters, ending abruptly against the fissures, as if someone ran a scalpel yesterday and tidied the edges. Around one fracture, a thin, dark mantle drapes the terrain, ignoring small undulations as if blown on minutes earlier, the kind of detail geologists use as a clock. If the dark carpet hasn't yet been peppered by many tiny craters, it hasn't had time to age. You don't need to force exact numbers to get the message. Compared to most of the planet, this is new. The label Young Seismicity was earned when the ground started talking to instruments. The InSight lander, parked hundreds of kilometers to the west, began hearing nighttime tremors repeatedly from the same direction. The signatures were consistent, small to moderate events, many with energy concentrated at lower frequencies, consistent with ruptures in warm rock or with dike accommodation. The persistent pattern pointed back to Cerberus Fossae. On calm nights, when wind wasn't rattling the seismometer, the tally rose, not by miracle, but because the environmental noise dropped and the Mars quakes revealed themselves. You can imagine the team's mixed frustration and excitement. A whole planet to choose from, and the one neighborhood still making noise is exactly the one that looks active on the map. What's driving the shaking? Put 3 pieces on the table and they fit. Dikes rising, regional stress tied to the weight of the Elysium volcanoes, and to interior cooling that pulls the carpet from below, and porous ground ice. A dike injects volume. It pushes sideways, cracks, and opens. The stress field sets the direction and spacing. It favors aligned cuts in bundles, regularly spaced as if the material obeyed an invisible grid. Ice, when present, becomes a multiplier. A bit of heat, a bit of friction, and pore spaces start venting vapor, which in turn boosts pressure where the rock is already weak. In the end, even if no magma ever sees daylight, the whole system moves enough to leave traces. Subsidence rims, fresh scarps, talus slopes with debris still lacking an old dust patina, and of course, a jolt when a section finally gives. This recent activity meshes with another Elysium Planitia signature, very young lava flows, some with the kneaded bread texture you'd expect in Icelandic basalt fields, not on Mars. There are channels that look like rivers, and many people once took them for rivers. But the full set of clues, sharp banks, elongated islands, chill ridges, fits better with floods of low-viscosity lava racing across gentle slopes. In certain outlets where the fossae meet these valleys, the story is almost didactic. The dike opens, the ground sags, the lava has a path. The flow runs for tens of kilometers and freezes into layers that from above resemble a wrinkled carpet. Crater counts on these carpets return numbers so short that in planetary terms, it's practically last week. Fine, it's new. So what? For anyone planning to operate there, new means unpredictable. On a world where almost everything is fossilized, any sign of ongoing process must be treated as a design variable. A fissure growing centimeters in a year won't show up on an orbital base map, yet it can reroute a rover. A dike advancing at depth can turn a flat stretch into a step with a 20-meter drop in a single season. A moderate quake, nothing that would fell a building on Earth, shakes blocks loose on slopes, redistributes debris, and lost dust to crash visibility to near zero at ground level. On Mars, where the air doesn't help damp vibrations and reduced gravity lengthens the fall of fragments, the afterquake is more showy than heavy. Lots of fine dust aloft, little pebbles rolling down ramps, and dry cascades that creep tens of meters and come to a slow stop. Then there's the treacherous topography of the fossae themselves. These aren't gentle ravines, they're cuts with straight rims, sometimes overhanging or sloped inward, that fail in slabs. Sand mantle sections, and from afar, fakes natural bridges. Up close, the cap hides voids, Martian rotten snow that accepts the first step and denies the second. Where fallen rim blocks have piled up, you get precarious ramps, faceted stones propped on one another at 3 points. A heavy rover leaning for support can turn the pile into a rolling die. There's little energy, but there's little friction too, and the slide travels meters before it ends. In terms of materials, Cerberus Fossae stacks roughnesses you don't get together elsewhere. Fractured basalt topped with ultra-dry fine sand. With no water and no wet electrostatic film like Earth's, the sand behaves like plastic beads. It charges readily, sticks in the wrong places, lofts easily, and when it settles, it thermally insulates whatever it blankets. For radiators, that's trouble. Dust becomes a blanket. For optical windows, it's cumulative blindness. And because charging grows with friction, every wheel turn, every leg step, every puff of gas to clean becomes a grain charging machine, exactly what you most want to avoid in your delicate mechanisms. Even the quiet hours play tricks. InSight's favorite Marsquakes arrived at night when the wind died. In the field, that translates to awkward logistics. The safest period to listen to what the ground is saying is the least comfortable period to operate. Thermally, night plunges temperatures. Energetically, solar panels sleep. Operationally, you do less. Yet those are the windows when vibration sensors, structure microphones, and accelerometric interferometers tell you what matters, where the quake came from, how deep, how frequent. In Cerberus Fossae, prudence wants the schedule tied to that clock. Measure a lot when you can hear, move little when the landscape is noisier, wind, dust, and above all, accept gaps when the atmosphere decides to interfere. Comparing to terrestrial rifts helps calibrate the mind without comforting the heart. In Iceland, plate boundaries open fissures, inject dikes, form lava lakes, vent gases, and trigger quake swarms. Icelanders live with it through robust engineering and dense monitoring. On Mars, you take away everyday liquid water, remove the other plate, lower gravity, dry the air, and you keep the skeleton of the process. Dike, fracture, quake. The lack of water doesn't eliminate risk, it changes its type. Explosions won't arrive as terrifying vapor columns, they'll come as dry jets, dust that rises without wind and falls slowly, crystals that glint in the low sun and then coat sensors. The sulfur smell won't reach you. The signal is seismic and optical, a REM that appeared where there wasn't one, shading that betrays fresh subsidence. There's a more conceptual point that makes Cerberus Fossae an uneasy place for the imagination. It disproves the idea that taming dust is enough to tame Mars. It isn't. Here, the subsurface keeps its own schedule. Plans that assume decades of stability for infrastructure, bases, cables, rails, roads, run into the real possibility of local tectonic rejuvenation. This isn't San Andreas and it isn't the East African Rift. It's millimeters per year or per season, a scale invisible to the human eye, but accumulated enough to change geometry, break alignments, stress pipes, crack platforms. And because the relief is low, any new step reshapes the hydrology of dust that nobody modeled. Wind finding a new channel, sand choosing a new path, and wind erosion descending along a fresh rim where none existed. It's impossible to skip the meeting of heat and ice because that gives substance to the word young. Martian ground ice, ice mixed into the soil, is a mechanical and chemical battery. Dikes and faults that cut into that stock change pressures, open pathways for localized thawing, and create transient episodes of supercooled liquid water at depth, quickly converted to vapor. That vapor seeks an exit, entrains grains, scours tubes, weakens roofs. A single small-scale cycle produces a dark halo around a fissure, a carpet of coarser particles left behind after the finest fraction was lofted away. On maps, it's a fresh signature. For operations, it's a warning. Beneath the halo, the roof has been working. You step onto the pretty part of the problem, the texture, and forget the problem itself. The temptation now would be to issue bans. Don't approach, don't cross, don't measure. That throws away the good part. Cerberus Fossae is a first-rate science target. It's where we study how a small, cooling planet still finds ways to concentrate heat and push magma, where we test how a dry body can nonetheless produce deposits that resemble ash, where we calibrate seismology for a world that doesn't shake much. It's the lab that turns Martian geology from museum into workshop. Respect here doesn't ask for retreat, it asks for method, a local seismic network instead of a single ear hundreds of kilometers away, distributed pressure and wind stations to separate shaking from gusting, thermal sentinels watching fissures to catch heat pulses that portray marching dikes, and imaging campaigns with repeated geometry, same angle, same local time, to flag subtle changes along the rims.